Welcome, fellow explorers. Tonight, we journey into the infinite cosmos, into the heart of the universe, where mysteries that have baffled humankind for centuries still await discovery. The universe, vast and boundless, holds secrets that stretch far beyond our imagination, and among these secrets, one stands out above all others. What is the largest planet ever discovered, and what does this tell us about the very nature of the cosmos itself? The universe is vast, far beyond our ability to comprehend. From the moment humans first gazed at the night sky, we've been fascinated by the stars, planets, and galaxies that dot the infinite expanse above us. In the early days of astronomy, we imagined a universe much simpler than what we now know it to be. However, with each new discovery, the universe has revealed itself to be an awe-inspiring, ever-expanding realm filled with mysteries and wonders we are only beginning to uncover. Among the greatest mysteries that have sparked the curiosity of astronomers is the question of the size and scale of planets, specifically the largest planet ever discovered in the universe. But before we dive into the discovery of the largest planet, it's important to understand what makes a planet large in the first place. In our everyday lives, we are familiar with the concept of size, whether it's the vastness of an ocean, the towering height of a skyscraper, or the immense size of the Earth. But in space, size takes on a whole new meaning. The vastness of the cosmos stretches far beyond the scale of our planet. To put it into perspective, Earth, with all its oceans, continents, and life, is a mere speck in the immensity of the universe. But even within our solar system, the planets vary drastically in size. From the relatively small, rocky planets like Mercury and Mars to the massive gas giants such as Jupiter and Saturn, our solar system is home to a remarkable variety of planetary sizes. Jupiter, the largest planet in our solar system, stands as a true giant. With a diameter of over 139,820 kilometers, more than 11 times that of Earth, it's hard to fathom the scale of such a planet. Its mass, more than 300 times that of Earth, and its vast atmosphere composed mostly of hydrogen and helium, make it a gas giant in every sense of the term. However, despite its immense size, Jupiter is far from the largest planet discovered in the universe. While it is a remarkable example of what a gas giant can be, it is but one of many. The discovery of exoplanets, planets orbiting stars beyond our solar system, has revealed planets far larger than even Jupiter, opening new frontiers in the study of planetary science. The search for the largest planets ever discovered has become one of the most exciting endeavors in modern astronomy. With the development of advanced telescopes and space exploration missions, scientists have begun to uncover planets that challenge our understanding of what is possible in terms of planetary size. These discoveries have not only expanded our knowledge of the universe, but have also raised new questions about the formation, composition, and behavior of such massive planets. What makes some planets grow to such enormous sizes, and what are the limits of their growth? How do these planets affect the systems they belong to? What can we learn from these giants that will help us understand the evolution of planets, stars, and galaxies? In this journey, we will explore the discovery of the largest planet ever found, delve into the science of planetary sizes, and learn about the factors that influence the growth of these giants. We'll investigate the methods astronomers use to detect and study exoplanets, and ultimately, we'll uncover the mysteries behind these colossal worlds. The search for the largest planet ever discovered is not just about size, it's about pushing the boundaries of our understanding and exploring the unknown. So let's begin our journey into the vast universe and uncover the giants that inhabit it. What makes a planet large? To understand what makes a planet truly large, we first need to understand how astronomers and scientists define size in the context of planets. In our everyday lives, when we think of something as being large, we typically consider its physical dimensions, height, width, and volume. However, in the cosmos, the definition of size can be much more complex. Size in planetary terms is not just about how big a planet appears, but also about its mass, volume, and the various forces that contribute to its overall characteristics. There are several factors to consider when defining a planet's size, including its diameter, mass, volume, and the composition of its atmosphere and surface. These elements together help us understand what makes a planet large in comparison to others. First, let's start with the simplest measurement, the diameter. The diameter of a planet refers to the straight-line distance across the planet, measured from one side to the other, passing through the planet's center. In a way, the diameter offers the most intuitive sense of a planet's size. For example, Earth has a diameter of about 12,742 kilometers, while Jupiter, the largest planet in our solar system, has a diameter of about 139,820 kilometers. The immense difference in diameter between Earth and Jupiter is a stark example of how large a planet can truly get. The sheer size of Jupiter alone is enough to make it more than 11 times wider than Earth. However, the diameter of a planet only tells part of the story. While a larger diameter does mean more space, it doesn't necessarily indicate a planet's mass. Mass is an essential factor in determining the size of a planet. In astronomical terms, mass refers to the amount of matter a planet contains, which is directly related to its gravity. The more mass a planet has, the stronger its gravitational pull, and the more likely it is to retain a thick atmosphere of gases or liquids around it. This gravitational force can also influence the planet's ability to hold onto its moons and prevent them from drifting away into space. While two planets may have the same diameter, the planet with more mass will exert a greater gravitational force and may appear larger in a different way. Take Jupiter and Saturn as examples. Despite having similar diameters, Jupiter has significantly more mass. Jupiter's mass is approximately 318 times that of Earth, while Saturn's mass is about 95 times that of Earth. This difference in mass contributes to Jupiter's ability to maintain its vast atmosphere, composed mostly of hydrogen and helium. The greater mass of Jupiter means it has a stronger gravitational pull, which helps it keep a much larger and denser atmosphere compared to Saturn. This difference in mass is a key factor in the distinction between what we might call a large planet and a giant planet. Next, we come to volume, which combines both the diameter and the density of a planet. The volume of a planet refers to the total space it occupies, and it's calculated based on its radius, half of the diameter. Volume gives us a sense of how much space a planet takes up, but it's important to note that volume and mass are not always directly correlated. For example, gas giants like Jupiter and Saturn are massive, but have relatively low density compared to rocky planets like Earth. This lower density is due to the composition of these planets. They are made mostly of gases such as hydrogen and helium, which are much less dense than rock or metal. Therefore, even though gas giants have enormous volumes, they do not necessarily have the same level of density as smaller, rockier planets like Earth, which are made up of much denser materials. The density of a planet plays a significant role in determining its overall characteristics. Planets that are made primarily of heavier elements like iron and rock tend to be denser and smaller in volume compared to planets that are composed mainly of lighter gases. Gas giants like Jupiter and Saturn, while vast in terms of volume, are less dense than Earth because the gases that make up their atmospheres are much lighter. The difference in density is one of the reasons why gas giants like Jupiter can be so massive but not necessarily have a corresponding mass-to-size ratio that matches rocky planets. In addition to size and mass, another key factor in defining a planet's size is its atmosphere. Planets with thick atmospheres, especially gas giants, can appear much larger than planets with thinner atmospheres. For example, While Jupiter's mass and diameter make it the largest planet in our solar system, its thick atmosphere, made of hydrogen, helium, and trace amounts of other gases, contributes significantly to its overall size. The planet's atmosphere is so massive and dense that it extends far beyond the planet's solid core, creating a vast, swirling gas giant that dwarfs Earth. The thick atmosphere also has an impact on the planet's weather patterns, temperature, and even its moons, as the gravity of the planet pulls on the gases and creates powerful storms, such as the Great Red Spot on Jupiter. However, the atmosphere also plays a critical role in the development and potential habitability of a planet. On Earth, our atmosphere is a delicate balance of gases that allow life to thrive. If a planet's atmosphere is too thin, it can lead to extreme temperatures and a lack of necessary gases like oxygen and nitrogen. On the other hand, if a planet's atmosphere is too thick or too dense, it can create an inhospitable environment, similar to what we see on Venus, where a runaway greenhouse effect has caused surface temperatures hot enough to melt lead. For gas giants like Jupiter, the thick atmosphere may not necessarily be a problem in terms of habitability. After all, no life as we know it could survive in such an extreme environment, but it still contributes to the planet's massive size. Another important factor in determining the size of a planet is the way it forms. Planet formation is a complex process that begins with the condensation of dust and gas in a protoplanetary disk around a star. As particles collide and stick together, they begin to form larger bodies. In some cases, this process continues until a planet forms that is small and rocky like Earth. In other cases, the process results in the formation of a gas giant, which can grow to immense sizes. The formation of gas giants, like Jupiter and Saturn, is thought to occur when a planet's core reaches a critical mass, allowing it to capture large amounts of gas from the surrounding nebula. This process leads to the formation of massive, low-density planets that can grow to tremendous sizes. But size is not just about the materials that a planet is made of. The environment surrounding a planet's star also plays a significant role in its growth. In some cases, planets are able to continue growing over time because they are located in star systems with abundant resources of gas and dust. Other planets, however, may stop growing once they reach a certain size, either because they have exhausted the available material or because the gravitational forces at play in their system no longer allow for further growth. The location of a planet in its star system, the type of star it orbits, and the presence of other nearby planets can all impact the planet's ability to grow and reach its full size. While size is important in defining what makes a planet large, it is also essential to remember that not all large planets are the same. Planets vary not just in their size, but also in their composition and characteristics. Some large planets are made mostly of gas, like Jupiter and Saturn, while others are primarily rocky or icy. Some have dense atmospheres, while others have barely any atmosphere at all. The nature of these planets and their environments is what makes them so fascinating to astronomers, who continue to study them in the hopes of learning more about the forces that shape planets, stars, and galaxies. As we move further into the exploration of exoplanets and the search for the largest planets in the universe, the question remains, how large can a planet truly get? What factors determine how big a planet can become before it reaches the limits of its growth? Is there an upper boundary to planetary size? These are questions that astronomers continue to explore, and the answers will undoubtedly provide us with new insights into the workings of our universe. For now, we have only scratched the surface of understanding what makes a planet large. But with each new discovery, we come closer to answering these profound questions. A brief history of planet discovery. The search for planets beyond our solar system, or exoplanets, has been one of the most exciting and significant developments in modern astronomy. While the discovery of exoplanets may seem like a recent achievement, the story of planetary discovery actually stretches back centuries, and it is rooted in our early understanding of the cosmos. To appreciate how far we've come in identifying the largest planets, it's important to understand the historical context of planetary discovery and the evolution of astronomical technology. The earliest humans observed the sky and noticed the wandering lights that moved differently from the fixed stars. These lights, which we now know to be planets, were visible to ancient astronomers and were often associated with the gods and mythological stories. For example, the ancient Greeks and Romans named planets after their gods: Jupiter, Saturn, Mars, Venus, and so on. These early astronomers recognized the movements of these planets, but they did not have the tools or knowledge to understand their true nature. For many centuries, the planets in our solar system were the only ones known to humanity. It wasn't until the 16th century that a major breakthrough occurred. In 1543, Nicolaus Copernicus proposed the heliocentric model of the solar system, which placed the Sun at the center of the universe and suggested that the planets, including Earth, revolved around it. This revolutionary idea challenged the geocentric view that had been dominant for centuries and laid the groundwork for future discoveries in astronomy. Copernicus' ideas were controversial at the time, but they eventually gained acceptance and set the stage for further developments in our understanding of planets. The next major breakthrough came with the invention of the telescope. In 1609, Galileo Galilei turned his newly constructed telescope toward the night sky and made a series of groundbreaking discoveries. He observed the moons of Jupiter, the phases of Venus, and the rings of Saturn. These observations provided strong evidence for the heliocentric model and furthered our understanding of the planets in our own solar system. Galileo's work marked the beginning of a new era in astronomy, where telescopes allowed for more detailed observations of planets and other celestial bodies. The development of telescopes and better observational techniques continued throughout the 17th and 18th centuries, leading to the discovery of more planets in our own solar system. In 1781, astronomer William Herschel discovered the planet Uranus, the first planet to be identified with a telescope that was not visible to the naked eye. This discovery was a milestone, as it expanded the known boundaries of the solar system. Later, in 1846, astronomers Johann Gottfried Galle and Heinrich Louis de Rest discovered Neptune, based on predictions made by mathematicians who noticed discrepancies in the orbit of Uranus. The discovery of Neptune confirmed the ability of mathematicians and astronomers to use observation and prediction to uncover new planets. Despite these significant discoveries within our own solar system, the idea of finding planets around other stars remained purely speculative for many years. The concept of exoplanets, planets orbiting stars outside our solar system, was proposed in the 16th century by the astronomer Johannes Kepler, who speculated that stars similar to the Sun would likely have planets of their own. However, it wasn't until much later that the technology and methods were developed to detect these distant worlds. The first hint of exoplanets came in the 1990s, when astronomers began using new observational techniques to search for planets orbiting other stars. The development of advanced telescopes, such as the Hubble Space Telescope, allowed scientists to study distant stars in greater detail. In 1992, two astronomers, Alexander Wolskson and Dale Frail, made the groundbreaking discovery of exoplanets orbiting the pulsar PSR B1257+12. This was the first confirmed detection of exoplanets, though they were not the kind of planets we typically think of. These planets were located around a pulsar, a type of neutron star, and were unlikely to support life due to the extreme conditions of their environment. The real breakthrough in exoplanet discovery came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of the first exoplanet orbiting a sun-like star, 51 Pegasi b. This planet, which is a gas giant similar in size to Jupiter, was found using a technique called the radial velocity method, which measures the slight wobble of a star caused by the gravitational pull of an orbiting planet. The discovery of 51 Pegasi b opened the floodgates to further exoplanet discoveries and ushered in a new era of planet hunting. The radial velocity method, also known as the Doppler method, remains one of the most important techniques for detecting exoplanets. By measuring the star's motion as it is tugged by the gravitational influence of an orbiting planet, astronomers can calculate the planet's mass and orbit. This method has been responsible for the discovery of thousands of exoplanets, some of which are larger than Jupiter and located far outside our solar system. In addition to the radial velocity method, another groundbreaking technique for detecting exoplanets is the transit method. This method involves measuring the dimming of a star's light as a planet passes in front of it, blocking a small portion of the star's light. By studying the amount of dimming, astronomers can determine the planet's size, orbit, and distance from its star. The Kepler Space Telescope, launched in 2009, used this method to discover thousands of exoplanets, many of which are Earth-sized or larger. Kepler's discoveries have revolutionized our understanding of planets, showing that planetary systems are common throughout the Milky Way galaxy. The discovery of exoplanets has revealed a diverse range of worlds, from small, rocky planets similar to Earth to massive gas giants that dwarf even Jupiter. One of the most exciting aspects of these discoveries is the identification of so-called super-Earths, planets that are larger than Earth but smaller than Uranus and Neptune. These planets, which may be rocky or have thick atmospheres, represent a new class of planets that could potentially support life or have environments unlike anything we've seen in our solar system. In the search for the largest planets, astronomers have identified several exoplanets that rival or exceed the size of Jupiter. One of the largest known exoplanets is HD 100,546b, which is located around 300 light-years from Earth. This planet is roughly 6.9 times the mass of Jupiter and is considered one of the most massive exoplanets ever discovered. Other massive exoplanets, such as WASP-17b and HD 106,906b, have also been found, each with unique characteristics that challenge our understanding of planetary formation and size. As we continue to improve our observational techniques, the search for even larger planets intensifies. With the advent of next-generation telescopes like the James Webb Space Telescope, which is set to launch in the near future, astronomers will have the ability to detect even smaller and more distant exoplanets with greater accuracy. These discoveries will undoubtedly provide more insights into the largest planets in the universe and help us answer questions about the limits of planetary size and what conditions lead to the formation of these giant worlds. The discovery of exoplanets has not only expanded our understanding of planets beyond our solar system, but has also raised new questions about the nature of the universe itself. What do these massive planets tell us about the evolution of planetary systems? How do they impact their star systems? And what do they reveal about the forces at work in the cosmos? As we continue to explore the universe and discover new planets, we move ever closer to answering these fundamental questions about the nature of the worlds that inhabit our galaxy. The role of exoplanet research. The discovery of exoplanets planets that exist outside our solar system has opened up entirely new frontiers in the study of astronomy. Prior to the 1990s, the idea of finding planets orbiting other stars was purely speculative. Ancient astronomers, including Johannes Kepler, suggested that stars similar to the Sun might host their own planets, but it wasn't until the development of new technologies and methodologies that the search for exoplanets became a real scientific endeavor. Today, exoplanet research stands at the cutting edge of space exploration, fundamentally reshaping our understanding of the universe and our place within it. Exoplanet research plays a pivotal role in several areas of astronomy and planetary science. Perhaps the most profound impact of exoplanet discovery is the way it has altered our understanding of how common planets are in the universe. The discovery of thousands of exoplanets, many of which exist in the habitable zones of their stars, has fueled the growing belief that planets are not unique to our solar system, but rather a ubiquitous feature of the cosmos. In fact, the Kepler Space Telescope alone has identified over 4,000 exoplanets since its launch in 2009, and this is just a fraction of the planets that likely exist throughout the Milky Way galaxy. The sheer number of planets discovered in such a short time has fundamentally changed how we think about the universe. One of the most significant outcomes of exoplanet research is the discovery of planets that could potentially support life. The term habitable zone refers to the region around a star where conditions might be just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. The discovery of Earth-like exoplanets in the habitable zones of their stars has sparked great excitement. Planets such as Kepler 452b, often dubbed Earth's cousin, lie within the habitable zone of their star, and though they may differ in other ways, their potential to harbor life has made them the subject of intense study. As we continue to discover more of these planets, scientists are beginning to develop ways to study their atmospheres and surface conditions in greater detail, bringing us closer to the ultimate question: are we alone in the universe? Exoplanet research has also significantly advanced our understanding of planetary formation. By studying the characteristics of exoplanets, astronomers can infer much about the processes that lead to planet formation. For instance, the discovery of planets with unusual characteristics, such as hot Jupiters, gas giants that orbit very close to their stars, has provided new insights into the dynamic processes that govern planetary evolution. These giant planets challenge traditional theories of planet formation, which suggested that gas giants could only form far from their parent stars. The existence of hot Jupiters suggests that planets can migrate within their solar systems over time, changing the way we think about the early stages of planetary system development. Additionally, the diversity of exoplanets discovered so far has revealed that planets come in all shapes and sizes, and many of them are unlike anything we see in our own solar system. From super-Earths, which are larger than Earth but smaller than Uranus or Neptune, to gas giants far larger than Jupiter, the variety of exoplanets has expanded our understanding of what is possible in terms of planetary composition, size, and location. Some exoplanets have been found to be extremely dense, while others are gas-rich giants with thick atmospheres. The range of exoplanet types discovered so far demonstrates that the process of planet formation is more complex and varied than previously thought. The search for the largest exoplanets in particular has captured the attention of astronomers. The discovery of massive planets, some of which dwarf even Jupiter, raises intriguing questions about the limits of planetary size and the processes that govern their formation. One key question that arises from the study of these supermassive planets is whether there is a limit to how large a planet can grow. Gas giants like Jupiter and Saturn are already massive by any standard, but astronomers have identified exoplanets like HD 100,546b, which are even larger. HD 100,546b, for example, is about 6.9 times the mass of Jupiter and is considered one of the most massive exoplanets discovered to date. This planet, along with others like WASP-17b and HD 106,906b, is challenging our understanding of the limits of planetary mass and the mechanisms that lead to the formation of such giants. In order to find and study these giant exoplanets, astronomers use several different methods. The most common techniques for detecting exoplanets are the transit method and the radial velocity method. The transit method involves monitoring a star for periodic dimming as a planet passes in front of it, blocking a portion of the star's light. This technique allows astronomers to measure the size, orbit, and distance of the planet from its star. The radial velocity method, on the other hand, measures the subtle wobbles in a star's movement caused by the gravitational pull of an orbiting planet. This wobble is incredibly small but detectable, and by analyzing it, astronomers can estimate the planet's mass and orbit. More advanced techniques, such as direct imaging and gravitational microlensing, are also used to detect exoplanets. Direct imaging involves capturing an image of the planet itself, which can be difficult because the light from the star often overwhelms the light from the planet. However, with the advent of new telescopes like the James Webb Space Telescope, astronomers will be able to capture clearer images of distant exoplanets and study their atmospheres in detail. Gravitational microlensing, on the other hand, occurs when the gravity of a star or planet magnifies the light of a distant background star, making it possible to detect planets that are otherwise too far away or faint to observe directly. One of the most exciting aspects of exoplanet research is the possibility of finding planets with conditions similar to those on Earth. While the discovery of life beyond Earth is still a distant goal, the detection of Earth-like planets in habitable zones has been one of the most exciting developments in the search for extraterrestrial life. In the coming years, astronomers will continue to refine their methods and tools, allowing them to find even smaller Earth-sized planets in the habitable zones of distant stars. These discoveries will not only deepen our understanding of planet formation, but will also provide insights into the potential for life beyond our solar system. As technology continues to advance, the study of exoplanets will only become more precise and detailed. The upcoming launch of the James Webb Space Telescope, for example, will allow scientists to study the atmospheres of exoplanets in unprecedented detail, searching for signs of life and analyzing the composition of these distant worlds. The continued development of ground-based telescopes and space observatories will also enable astronomers to detect exoplanets with greater sensitivity and accuracy, opening up new avenues for exploration. Exoplanet research has already transformed our understanding of the universe, and as more planets are discovered, it promises to reveal even greater insights into the nature of planetary systems, the potential for life elsewhere, and the processes that govern the formation and evolution of planets. The discoveries of the largest exoplanets, some of which are far larger than any planet in our solar system, are a testament to the incredible variety and complexity of the cosmos. As we continue to push the boundaries of technology and explore the far reaches of space, we may one day find answers to questions that have captivated humanity for centuries. Are we alone in the universe? What is the true extent of the planets and stars that make up the cosmos? And perhaps most intriguingly, how large can a planet really get? Introduction to the largest known planets. In the vastness of the universe, planets come in all shapes, sizes, and compositions. While we have become familiar with the planets in our solar system, the discovery of exoplanets has revealed a surprising variety of planetary types, including some that are vastly larger than those we are accustomed to. The search for the largest known planets has not only expanded our understanding of the universe, but has also raised profound questions about planetary formation, size limits, and the nature of planetary systems. The largest known planets discovered thus far are a category of planets that surpass our own Jupiter in size, mass, and sometimes even density. Jupiter, which is the largest planet in our solar system, is already a colossal body with a diameter of about 139,820 kilometers and a mass that is 318 times that of Earth. However, this giant planet is dwarfed by some of the massive exoplanets we have discovered in recent years, which offer new insights into the potential scale of planetary systems. These massive planets typically fall into two categories: gas giants and super-Earths. Gas giants, like Jupiter and Saturn, are primarily composed of hydrogen and helium and lack a solid surface. They can have enormous atmospheres stretching far out into space. On the other hand, super-Earths are rocky planets that are larger than Earth but smaller than Neptune and Uranus. These planets may have atmospheres similar to Earth, but are much more massive and have the potential to host unique environmental conditions. While Jupiter is often considered the benchmark for size in our solar system, it is by no means the largest planet ever discovered. Over the past few decades, astronomers have discovered a range of planets that far exceed Jupiter in both size and mass, some of which are located in distant star systems far beyond our own. These discoveries challenge our understanding of the limits of planetary size and the forces that contribute to a planet's growth. One of the first exoplanets that drew significant attention due to its immense size was the gas giant called HD 100,546b, discovered in 2005. HD 100,546b is located around 300 light-years from Earth in the constellation Musca. This exoplanet is approximately 6.9 times the mass of Jupiter, making it one of the largest known planets in terms of mass. HD 100,546b is still in the early stages of formation, and scientists believe it is surrounded by a massive disk of gas and dust, which it may continue to accrete over time, potentially increasing its size further. The planet's size and mass are remarkable not just because of the scale itself, but because they suggest that massive planets can form and exist in environments much different from what we see in our solar system. The discovery of HD 100,546b challenged existing theories of planetary formation, as astronomers had previously believed that planets of such mass would be incredibly rare, if not impossible to form. The planet's large size, combined with the unique properties of its atmosphere and environment, make it a fascinating subject for study. Another massive exoplanet that has captured the attention of astronomers is WASP-17b, which is located around 1,000 light-years from Earth in the constellation Scorpius. WASP-17b is a gas giant that is roughly twice the size of Jupiter, but has only half of its mass. This makes it an incredibly low-density planet, which is one of the defining features of gas giants. WASP-17b is part of a class of planets known as ultra-low-density planets, which are planets that are so large but have such low mass that their density is extremely low compared to that of Earth. This low density is a result of the planet's massive atmosphere, which is composed mostly of hydrogen and helium. WASP-17b is particularly interesting to scientists because it challenges our understanding of how planets can form and retain their size. Its size and low density suggest that gas giants may be able to grow much larger than we previously thought, as long as they have the right conditions. The planet's discovery has led to new models of gas giant formation, which suggest that these planets may be able to accumulate mass at a faster rate than we had once assumed. WASP-17b's large size, combined with its low mass, raises intriguing questions about the mechanics of planetary growth and the role of gravity in shaping the size of gas giants. In addition to gas giants, there are also super-Earths, which are rocky planets that are larger than Earth but smaller than Neptune and Uranus. These planets have attracted significant interest from scientists because they could potentially harbor life, and they also provide valuable insights into planetary formation and the conditions required for a planet to support an atmosphere. One of the most well-known super-Earths is Kepler 452b, which was discovered in 2015 by NASA's Kepler Space Telescope. Kepler 452b is about 60% larger than Earth and is located in the habitable zone of its star, which means it is at the right distance for liquid water to exist on its surface, a key ingredient for life as we know it. Kepler 452b is often referred to as Earth's cousin because of its similarities to Earth in terms of size, location, and the possibility that it could have conditions suitable for life. However, despite these similarities, Kepler 452b is likely very different from Earth in many ways. Its larger size could mean that its atmosphere is much thicker, which would result in different environmental conditions. Furthermore, its star, a slightly older and brighter version of our Sun, may emit higher levels of radiation, which could affect the potential for life on the planet. Another fascinating super-Earth is LHS 1140b, which was discovered in 2017 and is located about 40 light-years from Earth in the constellation Cetus. LHS 1140b is about 1.4 times the size of Earth and is located in the habitable zone of its star, making it another candidate for the search for extraterrestrial life. The planet is rocky and has a solid surface, unlike the gas giants, and scientists believe that its atmosphere could contain a mix of gases that may support life. The discovery of LHS 1140b has sparked interest in the search for other potentially habitable planets, and scientists are eager to study this super-Earth further in the coming years. The diversity of the largest known planets is a testament to the variety of planetary systems that exist in the universe. While gas giants like Jupiter and Saturn are the most well-known large planets, the discovery of super-Earths and ultra-low-density planets has expanded our understanding of the different types of planets that can form. These planets come in many different shapes and sizes, and their characteristics depend on a range of factors, including their distance from their star, the composition of their atmosphere, and the forces at work during their formation. The discovery of these massive exoplanets has profound implications for our understanding of planetary systems and the conditions required for life. The sheer size of some of these planets challenges our previous conceptions of planetary formation, and they offer valuable insights into the processes that govern the evolution of stars and planets. As we continue to refine our observational techniques and improve our telescopes, it is likely that we will continue to uncover even larger planets and more diverse planetary systems. One of the most exciting aspects of the study of large exoplanets is the potential for future discoveries. As technology continues to improve, astronomers will be able to detect even smaller and more distant exoplanets. And with the help of powerful telescopes like the James Webb Space Telescope, we may soon be able to study the atmospheres of these planets in detail. These discoveries will not only help us learn more about the largest planets, but also provide insights into the formation of planetary systems, the conditions required for life, and the possibility of finding Earth-like planets in the far reaches of space. This is Chunk 5, which introduces the largest known planets and explores some of the massive exoplanets that have been discovered. Let me know if you'd like me to continue with the next chunk or make any adjustments. Next, here's Chunk 6, focusing on the search for the largest planet. Chunk 6, the search for the largest planet. The search for the largest planet ever discovered is one of the most exciting and ongoing endeavors in the field of astronomy. The universe is vast, and our ability to detect and study exoplanets has expanded tremendously in the last few decades. As our telescopes become more sophisticated and our techniques more refined, astronomers are able to find planets that are not only larger than anything we imagined, but are also revealing the extreme diversity of planetary types that exist in distant star systems. The search for these massive worlds challenges our understanding of planetary formation and the limits of size, while also providing a wealth of new data that could answer fundamental questions about how planets form and evolve. One of the primary challenges in the search for the largest planets is the sheer distance involved. Exoplanets are often located light years away from Earth, making it difficult to observe them directly. In many cases, the planets themselves are too faint to be seen with our current telescopes, meaning astronomers must rely on indirect methods of detection. The two most common methods for discovering exoplanets are the radial velocity method, also known as the Doppler method, and the transit method. Both of these methods allow astronomers to infer the existence of planets by studying the effects they have on their parent stars, but they also have their limitations. The radial velocity method works by measuring the small wobble in a star's position caused by the gravitational pull of an orbiting planet. As the planet orbits its star, it exerts a gravitational force that causes the star to move slightly in response. By measuring these shifts in the star's motion, astronomers can calculate the planet's mass and orbit. This method has been incredibly successful in detecting large exoplanets, particularly gas giants, because the more massive a planet is, the greater its gravitational influence on its parent star. However, the radial velocity method is limited by the fact that it can only detect the gravitational wobble of a star, which means that smaller planets, especially rocky ones like Earth, are more difficult to detect. Additionally, this method doesn't provide direct information about the size or composition of the planet itself, which means astronomers must use other techniques to gather more detailed data about these distant worlds. The transit method, on the other hand, involves observing the dimming of a star's light as a planet passes in front of it, blocking a small portion of the star's light. This method is especially useful for detecting planets that are in close orbits around their parent stars, as the planet regularly passes in front of the star, causing periodic dips in brightness. By measuring the amount of light blocked and the duration of the transit, astronomers can determine the planet's size, distance from its star, and orbital period. The transit method has been particularly successful in detecting large planets, especially those that are similar in size to Jupiter or even larger. In fact, many of the largest exoplanets ever discovered have been found using this technique, including planets that are much larger than Jupiter and located in distant star systems. While the transit method is more effective at detecting larger planets, it is also limited by the fact that the planet must be aligned in such a way that it passes directly between the observer and its star. If the planet's orbit is tilted, or if the planet is located too far from its star, the transit method may not be able to detect it. Another method that has shown promise in the search for large planets is direct imaging. Direct imaging involves capturing an image of a planet itself, rather than inferring its presence through the effects it has on its star. This method is particularly useful for detecting large planets that are located far from their parent stars, as their brightness can be more easily distinguished from the light of the star. However, direct imaging is still in its early stages and requires incredibly sophisticated technology to isolate the light from the planet itself, especially when the planet is very distant and faint. One of the most important tools in the search for large planets is the use of space telescopes. Telescopes like the Hubble Space Telescope, launched in 1990, have played a crucial role in the discovery of many exoplanets, including some of the largest known. Hubble has allowed astronomers to study distant star systems in unprecedented detail and has provided the first direct observations of exoplanet atmospheres. The Kepler Space Telescope, launched in 2009, took the search for exoplanets to new heights by scanning the sky for planetary transits, ultimately identifying thousands of new exoplanets, including many that are much larger than Jupiter. Kepler's discoveries have expanded our knowledge of the size and diversity of planets in the universe, and it has also provided new insights into the formation and evolution of these distant worlds. As we move into the next decade, new telescopes, such as the James Webb Space Telescope, JWST, are expected to revolutionize the search for large planets. JWST, which is set to launch in the near future, will be able to observe exoplanets with greater sensitivity and precision than ever before. One of JWST's key goals is to study the atmospheres of exoplanets, particularly those in the habitable zone of their stars. By analyzing the light passing through an exoplanet's atmosphere during a transit, astronomers will be able to identify the gases that make up the atmosphere and look for signs of chemical compositions that might indicate the presence of life. JWST will also be able to study the largest exoplanets in greater detail, allowing astronomers to investigate their atmospheres, compositions, and even their weather systems. These observations will be crucial in understanding the conditions on these massive planets and whether they could support life or unique environmental conditions. By studying the largest planets, scientists hope to learn more about how planets form, how they evolve, and what factors influence their growth and size. The search for the largest planet also raises important questions about the limits of planetary size. How big can a planet really get? Is there an upper limit to how massive a planet can become? As we discover more giant exoplanets, astronomers are beginning to explore these questions in greater depth. Some of the largest planets, such as HD 100,546b and WASP 17b, have already surpassed the size and mass of Jupiter, and the discoveries continue to push the boundaries of what we thought was possible in planetary formation. Theoretical models of planet formation suggest that there may be a physical limit to how large a planet can grow, as the processes that lead to the accumulation of mass may become less efficient at larger sizes. These models predict that planets much larger than Jupiter could become unstable and break apart due to the intense gravitational forces at play. In the coming years, as technology improves and new telescopes are launched, we will continue to search for even larger planets, expanding our knowledge of the universe and testing the limits of planetary formation. Whether through the transit method, radial velocity, direct imaging, or future techniques, astronomers are committed to uncovering the most massive and distant planets ever discovered. These discoveries will not only help us understand the forces that shape planetary systems, but will also reveal more about the nature of the universe itself. What makes some planets so massive? As we look further into the cosmos and discover increasingly massive planets, one question naturally arises. What exactly allows some planets to grow to such enormous sizes? Why are some planets, like Jupiter, Saturn, and even larger exoplanets, so much more massive than others, such as Earth or Mars? What factors contribute to a planet's size, and how do certain environments facilitate the creation of planets that defy our understanding of the limits of planetary growth? Understanding the formation of massive planets requires delving into the processes of planetary creation, the physics that govern these processes, and the conditions necessary for planets to grow to such incredible sizes. One of the primary factors that determine a planet's size is its mass. In planetary science, mass plays a crucial role in shaping the characteristics of a planet. The more mass a planet has, the more gravity it exerts. This increased gravity allows the planet to pull in more material from its surrounding environment, enabling it to continue growing. Gravity is the fundamental force that governs the accretion of gas and dust during the planet formation process. The more mass a planet accumulates, the more gas it can attract from the surrounding nebula, eventually growing into a gas giant like Jupiter or Saturn. The formation of massive planets begins with the condensation of dust and gas in a protoplanetary disk. This disk forms around a newly formed star and is composed of small particles of rock, ice, and gas. Over time, these particles collide and stick together, forming larger and larger bodies. These growing bodies are called planetesimals. As planetesimals accumulate more material, they eventually become protoplanets, the precursors to full-fledged planets. The process of accretion allows these bodies to gather more gas and dust, eventually forming planets of varying sizes. However, the process by which a planet gathers mass isn't always straightforward. Some planets, especially gas giants, continue to grow long after their initial formation. In the case of Jupiter, for example, scientists believe that its core grew to a critical mass before it was able to attract large amounts of gas from the surrounding nebula. This allowed Jupiter to continue growing far beyond the size of the rocky planets in our solar system. The combination of a massive core and a strong gravitational pull enabled Jupiter to accumulate vast amounts of hydrogen and helium, two of the lightest elements in the universe, resulting in the formation of a massive, low-density atmosphere. In addition to the initial accumulation of material, the environment in which a planet forms plays a key role in determining how massive it can become. The presence of nearby gas and dust, the mass and type of the parent star, and the temperature of the surrounding region all influence the final size of a planet. Planets that form closer to their parent star, where the temperature is higher, may not be able to accumulate as much gas due to the intense heat, which can cause lighter gases like hydrogen and helium to escape into space. However, planets that form farther away from their star, in the colder regions of a star system, can retain large amounts of gas and grow to much larger sizes. The presence of a massive star also plays an important role in the growth of large planets. In star systems with massive stars, the increased gravitational pull can cause the surrounding nebula to collapse more quickly, providing more material for planets to form. This faster rate of accretion allows planets to grow more quickly and reach larger sizes before the available material runs out. On the other hand, star systems with smaller stars may not produce as much material for planet formation, limiting the potential size of planets in those systems. One of the most intriguing factors that contributes to the size of some planets is the role of planetary migration. Planets don't always stay in the positions where they originally formed. In some cases, massive planets like Jupiter may migrate inward toward their parent star, a phenomenon known as planetary migration. This migration can occur as a result of gravitational interactions with other planets in the system, or through interactions with the protoplanetary disk itself. The migration of giant planets can have dramatic effects on the rest of the star system, including the redistribution of smaller planets, asteroids, and comets. This migration process can also result in the formation of large, massive planets in regions that might not otherwise be able to support them. In some cases, the migration of a massive planet can lead to the formation of additional planets. For example, if a planet migrates inward toward its star, it may capture gas and dust from the protoplanetary disk, enabling it to grow even larger. In systems where multiple planets form at once, the gravitational interactions between the planets can cause them to migrate to new orbits, sometimes resulting in the formation of even larger planets. These interactions can lead to systems where massive gas giants, like Jupiter and Saturn, coexist with smaller rocky planets or icy worlds. Another fascinating factor in the formation of massive planets is the phenomenon of runaway gas accretion. This occurs when a planet has already grown to a certain size and mass, allowing it to accumulate gas at an accelerated rate. As the planet's gravity becomes stronger, it is able to capture more and more gas from its surroundings, which allows it to continue growing rapidly. This process is thought to be one of the key mechanisms behind the formation of gas giants like Jupiter and Saturn. In some cases, runaway gas accretion can lead to the rapid formation of planets that are much larger than what we would expect based on traditional models of planetary growth. The size of a planet also depends on its composition. Gas giants like Jupiter and Saturn are primarily composed of hydrogen and helium, which are light elements, and their large size is a result of the accumulation of these gases. In contrast, terrestrial planets like Earth, Venus, and Mars are made up of heavier elements like iron, rock, and metal. These planets are smaller in size because heavier elements are denser and do not easily form thick atmospheres. While gas giants can grow to enormous sizes due to the accumulation of light gases, rocky planets are more limited in their growth due to the physical properties of the materials they are made from. Super-Earths, which are planets larger than Earth but smaller than Neptune or Uranus, provide a unique opportunity to study the factors that contribute to planetary size. These planets are made up of rock, ice, and gas, and their size likely results from a combination of factors, including the amount of material available in their star systems, their distance from their parent star, and the type of star they orbit. Some super-Earths may have atmospheres that are thick and rich in gases, while others may have thinner atmospheres similar to Earth's. The composition and size of these planets make them intriguing targets for study, as scientists continue to explore how planets of this size form and whether they might harbor the conditions necessary for life. The formation of massive planets is also closely tied to the physical conditions within a star system. The amount of material available in a star system, the presence of other planets, and the interactions between the various objects in the system all play a role in determining how massive a planet can become. In some systems, massive planets form early and have the opportunity to grow to incredible sizes, while in other systems, planets may be more limited in their growth due to a lack of available material or the presence of other planetary bodies. In conclusion, the process of planetary formation is complex and multifaceted, and the factors that contribute to the creation of massive planets are still not fully understood. From the initial accumulation of material in a protoplanetary disk to the influences of nearby stars, gravity, and planetary migration. Many different factors come into play when it comes to the size of a planet. The discovery of large exoplanets challenges our understanding of the limits of planetary growth and raises new questions about how planets form, how they evolve, and what factors determine their size. As we continue to explore the universe and discover new planets, we will undoubtedly learn more about the processes that govern planetary formation and the forces that allow some planets to grow to such massive sizes. This is Chunk 7, focusing on what makes some planets so massive. Let me know if you'd like to proceed with the next chunk or make any changes. Next, certainly, here's Chunk 8, focusing on Introduction to HD 100546b. Chunk 8, Introduction to HD 100546b. Among the many fascinating exoplanets discovered in recent years, one that stands out for its size, composition, and unique characteristics is HD 100546b. This massive planet, located approximately 300 light-years away in the constellation Musca, has captured the attention of astronomers due to its sheer size, unusual features, and the mysteries surrounding its formation. As one of the largest exoplanets discovered so far, HD 100546b presents an incredible opportunity for scientists to study planetary formation on a grand scale and to learn more about the extreme environments in which massive planets can form. HD 100546b is located in a region of space known as a protoplanetary disk, a swirling disk of gas, dust, and other materials that surround young stars. These disks are the birthplaces of planets, where the initial accretion of material gradually forms planetesimals and eventually full-fledged planets. HD 100546b's location within such a disk is key to understanding its massive size and ongoing development. The planet is still in the early stages of its formation, and scientists believe that it is actively accumulating material from the surrounding disk, which could allow it to grow even larger over time. The star at the center of the system, HD 100546, is a young A-type star, much larger and hotter than our Sun. This type of star is known for emitting large amounts of ultraviolet radiation, which has a significant impact on the protoplanetary disk. The strong radiation from the star could influence the rate at which material accretes onto HD 100546b, potentially leading to its growth into one of the largest planets ever discovered. The intense radiation may also contribute to the planet's unique atmospheric composition and the extreme conditions observed on its surface. One of the most fascinating aspects of HD 100546b is its size. Estimates suggest that the planet is roughly 6.9 times the mass of Jupiter, making it one of the largest planets ever observed in terms of mass. While it is still a gas giant, similar to Jupiter and Saturn, the sheer mass of HD 100546b raises intriguing questions about how planets of such size can form and what conditions are necessary for their growth. The planet's mass is so large that it challenges our current understanding of the limits of planetary formation, and it may provide valuable insights into the processes that lead to the creation of supermassive planets in other star systems. The discovery of HD 100546b was made using a variety of observational techniques, including direct imaging and spectroscopy. Direct imaging involves capturing an image of the planet itself, which is an incredibly challenging task given the vast distances between Earth and distant exoplanets. However, thanks to the development of advanced space telescopes, astronomers were able to observe the planet by blocking out the light from the parent star and isolating the faint light emitted by the planet. This allowed scientists to measure the planet's size, mass, and other characteristics, providing valuable data on its composition and atmosphere. In addition to its size, HD 100546b is noteworthy for its unusual atmosphere. The planet is surrounded by a thick atmosphere composed primarily of hydrogen and helium, similar to other gas giants. However, the atmosphere of HD 100546b is thought to be much more dynamic than those of planets like Jupiter or Saturn. The planet's massive size and strong gravitational field allow it to retain a large and dense atmosphere, which is constantly undergoing changes due to the extreme conditions in the star system. This dynamic atmosphere is a key area of interest for astronomers, as it could provide valuable insights into the processes that govern the behavior of gas giant atmospheres. Another remarkable feature of HD 100,546b is its orbital characteristics. The planet orbits its star at a distance that is much greater than that of Earth from the Sun, but still close enough to be influenced by the star's intense radiation. Its orbit is not perfectly circular, but rather an eccentric orbit, meaning that the distance between the planet and its star changes over time. This eccentricity could affect the planet's atmosphere and climate, as well as its ability to retain gas and other materials from the surrounding disk. The changing distance from the star could also play a role in the planet's long-term growth and development, as it may influence the rate at which material accretes onto the planet. One of the most intriguing aspects of HD 100,546b is the fact that it is still forming. While the planet has already reached a massive size, it is located in a region of space where it can continue to grow by accreting material from the surrounding disk. This ongoing growth process makes HD 100,546b a unique target for study, as it provides astronomers with a glimpse into the early stages of planetary formation. By observing this planet and its protoplanetary disk, scientists hope to learn more about how planets of this size come into being, what conditions are necessary for their growth, and whether there are other planets like HD 100,546b in the universe. The study of HD 100,546b could also provide valuable insights into the formation of planetary systems. While the planet itself is massive, the surrounding protoplanetary disk is also rich in material, and it is possible that other planets are forming in the same system. The study of this disk and the interaction between the disk and the planet could reveal important information about the processes that govern the formation of planetary systems, including the distribution of mass, the role of stellar radiation, and the migration of planets within their star systems. As we continue to learn more about HD 100,546b, it is clear that this planet will play a crucial role in advancing our understanding of planet formation. The fact that it is still growing and evolving offers astronomers a rare opportunity to study a planet in the process of becoming a giant, shedding light on the complex dynamics that govern the formation of gas giants and other massive worlds. By studying this planet in detail, we can not only learn more about the processes that shape planets, but also gain valuable insights into the evolution of planetary systems and the conditions necessary for life to exist elsewhere in the universe. In the coming years, as astronomers continue to observe HD 100,546b and other massive exoplanets, we will likely uncover even more secrets about the nature of planetary formation and the limits of planetary size. As technology improves and new telescopes, like the James Webb Space Telescope, come online, we will have the ability to study planets like HD 100,546b in greater detail, unlocking new insights into the processes that govern the creation and evolution of worlds. The discovery of such massive planets not only challenges our understanding of the universe, but also raises important questions about the nature of planetary systems and the potential for life beyond Earth. The discovery of HD 100,546b. The discovery of HD 100,546b represents a significant milestone in the study of exoplanets, particularly when it comes to the largest and most massive planets ever observed. Located in the constellation Musca, about 300 light-years away from Earth, HD 100,546b is one of the most remarkable planets found to date due to its size, young age, and the intriguing mysteries it presents to astronomers. The process of its discovery and the groundbreaking research surrounding it have shed new light on the nature of planet formation, the role of gas giant planets in young star systems, and the vast potential for discovering similar worlds in the universe. HD 100,546b was discovered as part of an ongoing effort to study young star systems with the help of modern space telescopes and ground-based observatories. The planet orbits around HD 100,546, a relatively young, hot star about 1.5 times the mass of our Sun. This star is part of a system that is still in the process of formation, and its surrounding protoplanetary disk is rich in the gas and dust that will eventually coalesce into planets, moons, and other objects. The discovery of HD 100,546b is significant because it is located within this active star-forming region, where planets are still growing and material is constantly being added to the disk. As such, HD 100,546b represents a rare opportunity to study a planet in the early stages of its formation. It is believed that HD 100,546b is still in the process of accumulating material from the surrounding disk, which makes it a dynamic and evolving object in the universe. While many exoplanets are found around older stars, where planetary systems have already formed and settled into a relatively stable state, HD 100,546b offers astronomers a unique chance to observe a planet as it continues to grow and change. The discovery of HD 100,546b was made using a variety of advanced observational techniques, including direct imaging, which allows scientists to capture an image of the planet itself by blocking out the bright light from its parent star. Direct imaging is an incredibly challenging method for detecting exoplanets, especially those located far from their stars, as the light from the parent star often overwhelms the much dimmer light emitted by the planet. However, with the advent of modern space telescopes and specialized techniques, astronomers were able to successfully capture images of HD 100,546b, making it one of the few exoplanets to be observed directly. The use of spectroscopy played a crucial role in confirming the discovery, and studying the properties of HD 100,546b spectroscopy is a technique that analyzes the light emitted by a planet and its atmosphere, breaking it down into its constituent wavelengths. By studying the spectral signature of the planet, astronomers can determine its composition, temperature, and other physical properties. In the case of HD 100,546b, spectroscopy revealed that the planet is a gas giant, composed mainly of hydrogen and helium, similar to Jupiter and Saturn in our solar system. One of the key factors that made HD 100,546b's discovery so exciting was the planet's massive size. It is approximately 6.9 times the mass of Jupiter, making it one of the largest exoplanets ever discovered. The discovery of such a massive planet in a relatively young star system raised important questions about how planets of such enormous size could form in the first place. Most planets that are discovered, even massive gas giants, tend to have much smaller masses, often in the range of 1–2 times the size of Jupiter, HD 100,546b's massive size challenged traditional models of planet formation, which suggested that gas giants should not grow to such extreme sizes in the early stages of their formation. The planet's large size is not the only remarkable feature. HD 100,546b's location in the protoplanetary disk of its star system also contributes to its unusual characteristics. In many other star systems, gas giants like Jupiter and Saturn formed much earlier in the system's evolution and became relatively stable after they finished growing. However, HD 100,546b is still in the process of accreting material, and its environment is far from stable. The planet's mass continues to grow as it pulls in gas and dust from the surrounding disk, and it is possible that HD 100,546b will continue to grow and evolve for millions of years. The disk surrounding HD 100,546 is rich in gas and dust, and scientists believe that the planet is still actively feeding off the material around it. This dynamic environment makes HD 100,546 be an exceptional target for studying the process of planet formation and the mechanisms that govern the growth of gas giants. The fact that the planet is still growing means that it is likely to remain an important object of study for many years to come. As astronomers continue to monitor the planet and its surroundings, they hope to learn more about the factors that contribute to the growth of massive planets and the ultimate limits of planetary size. The discovery of HD 100,546b also raised important questions about the formation of planetary systems as a whole. As the planet continues to grow, it exerts significant gravitational forces on the surrounding material, and this may affect the development of other planets or moons in the system. In particular, astronomers are interested in how the planet's growth influences the migration of other objects in the protoplanetary disk. The interactions between HD 100,546b and its disk could provide valuable insights into the ways that planets migrate within their star systems and the role that migration plays in the formation of planetary systems. Another fascinating aspect of HD 100,546b's discovery is the fact that it is part of a growing body of evidence suggesting that massive planets may be more common than previously thought. Prior to the discovery of HD 100,546b and other massive exoplanets, astronomers believed that large planets were relatively rare in the universe. However, as more and more massive exoplanets are discovered, it is becoming clear that gas giants like HD 100,546b are not anomalies, but rather part of a larger trend in the formation of planetary systems. These discoveries are helping astronomers refine their models of planet formation and better understand the diversity of planetary systems that exist in our galaxy. The discovery of HD 100,546b also illustrates the power of modern astronomical instruments and techniques. The ability to observe distant exoplanets directly using methods like direct imaging and spectroscopy has revolutionized our understanding of the universe and our place in it. Instruments like the Hubble Space Telescope, VLT, Very Large Telescope, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have enabled astronomers to study exoplanets in unprecedented detail, revealing the complex and diverse nature of planets outside our solar system. With the upcoming launch of the James Webb Space Telescope, JWST, astronomers will gain even more advanced tools to study planets like HD 100,546b and other exoplanets, which will likely lead to new discoveries and insights about the nature of planetary systems. In the coming years, as technology advances and more observations are made, the study of HD 100,546b will continue to shape our understanding of planet formation. This planet's size, environment, and ongoing development make it an important subject for scientists seeking to understand the limits of planetary growth and the processes that govern the evolution of gas giants. Whether through direct imaging, spectroscopy, or future space telescopes, HD 100,546b will remain a key player in the ongoing quest to uncover the mysteries of the universe and the planets that populate it. The size and composition of HD 100,546b. HD 100,546b is a truly remarkable exoplanet, both in terms of its size and its composition. As one of the largest exoplanets discovered to date, it has fascinated astronomers and planetary scientists alike. The planet's size, which is approximately 6.9 times the mass of Jupiter, makes it one of the most massive gas giants ever observed, and its composition holds clues to understanding the formation and evolution of planetary systems. In this section, we will explore the size and composition of HD 100,546b, looking at its mass, atmosphere, and the factors that influence its development. Size and mass. The size of HD 100,546b is one of the most striking features of the planet. With a mass of about 6.9 times that of Jupiter, HD 100,546b is an immense gas giant that far exceeds the size of any planet in our solar system, except for Jupiter itself. For comparison, Jupiter's mass is about 318 times that of Earth, and Saturn, the second largest planet in our solar system, has a mass that is roughly 95 times that of Earth. Despite being smaller than Jupiter in terms of its size, HD 100,546b's mass is a significant indicator of its size and the forces at play in its formation. The mass of a planet is closely linked to its gravity, which influences not only the planet's overall size, but also its ability to retain an atmosphere, its formation process, and the dynamics of the planet's surrounding environment. HD 100,546b's immense mass suggests that it likely possesses an extraordinarily strong gravitational field, which has allowed it to retain a massive and dense atmosphere made primarily of hydrogen and helium. This is consistent with what we would expect from a gas giant, where the planet's gravity is strong enough to trap large amounts of these light gases, preventing them from escaping into space. The planet's size also raises important questions about the limits of planetary growth. While HD 100,546b is far larger than Jupiter, it is not an outlier in terms of gas giant formation. In fact, it is part of a growing category of exoplanets known as superjupiters, which are gas giants that are significantly more massive than Jupiter. The discovery of superjupiters, like HD 100,546b, challenges the traditional models of planetary formation, as it was once believed that planets of such massive sizes were unlikely to form or would face significant challenges during their development. However, the existence of such planets suggests that there are conditions in some star systems that can lead to the formation of truly massive worlds. Composition. The composition of HD 100,546b is primarily made up of light elements such as hydrogen and helium, typical of gas giants in our solar system. Like Jupiter and Saturn, HD 100,546b likely lacks a solid surface and instead has a thick, dense atmosphere that gradually transitions into a deep, featureless gaseous interior. The planet's composition is not uniform, however. Astronomers believe that HD 100,546b may have a core made of heavier elements such as iron and rock, similar to the cores of other gas giants. The core of a gas giant is often surrounded by layers of hydrogen and helium, with increasing pressure as one moves deeper into the planet's interior. One of the most important aspects of HD 100,546b's composition is the fact that it is still in the process of accreting material from the surrounding protoplanetary disk. This means that the planet is actively pulling in gas, dust, and other materials from the disk, which will likely contribute to its growth in the coming millions of years. The composition of the surrounding disk plays a key role in determining the types of materials that HD 100,546b will accrete as it grows. The star at the center of the system, HD 100,546, is an A-type star that is much larger and hotter than our Sun, emitting large amounts of ultraviolet radiation. This radiation affects the surrounding disk, influencing the types of elements that are present and the rates at which they condense and accrete onto the planet. The fact that HD 100,546b is still growing and accreting material makes its composition particularly interesting to study. As it continues to draw in gas and dust from the surrounding disk, the planet's atmospheric composition may change over time. For example, the planet may accumulate heavier elements that could eventually form ice and rock layers, leading to a more complex internal structure. The ongoing process of accretion also makes HD 100,546b a unique target for studying the dynamics of gas giant formation and the factors that determine a planet's composition at various stages of its growth. Atmosphere. The atmosphere of HD 100,546b is one of the most intriguing aspects of the planet, and it is a subject of intense study for astronomers. As a gas giant, HD 100,546b's atmosphere is likely composed mainly of hydrogen and helium, with trace amounts of other gases, such as methane, ammonia, and water vapor. However, the exact composition of the planet's atmosphere is still a subject of ongoing research. One of the challenges of studying the atmosphere of such distant exoplanets is the fact that their light is often overwhelmed by the brightness of their parent star. To overcome this, astronomers use techniques such as direct imaging and spectroscopy to analyze the light from the planet and extract information about its atmosphere. One of the key features of HD 100,546b's atmosphere is its dynamic nature. The planet's size and mass allow it to retain a thick and dense atmosphere, but the environment surrounding the planet is anything but stable. The star's intense ultraviolet radiation influences the planet's atmosphere, causing it to undergo constant changes. The presence of a massive protoplanetary disk around the star also adds to the dynamic nature of the planet's atmosphere, as material from the disk may be continually interacting with the atmosphere, creating fluctuations in temperature, composition, and pressure. Additionally, the planet's eccentric orbit adds another layer of complexity to its atmospheric dynamics. As HD 100,546b moves closer and farther from its parent star during its orbit, the planet's atmosphere will experience changes in temperature and radiation. This could lead to shifting weather patterns, with areas of the planet becoming hotter or cooler depending on its position in its orbit. The eccentricity of the planet's orbit could also influence the planet's overall climate, affecting the types of gases that are present in the atmosphere at different times. Atmospheric modeling and future studies. The study of HD 100,546b's atmosphere is ongoing, and astronomers are particularly interested in learning more about the chemical composition and physical conditions that exist on the planet. Using tools like the Hubble Space Telescope, astronomers are able to study the absorption spectra of the planet's atmosphere, which can reveal the presence of certain gases and elements. By analyzing the spectrum of light that passes through the planet's atmosphere, scientists can also determine the temperature, pressure, and chemical makeup of the atmosphere. The upcoming launch of the James Webb Space Telescope, JWST, promises to offer even more advanced tools for studying exoplanet atmospheres. JWST's ability to observe exoplanets in the infrared will allow scientists to gather more detailed information about the temperature and composition of HD 100,546b's atmosphere. JWST's advanced spectroscopic capabilities will also provide new insights into the presence of molecules like water vapor, methane, and carbon dioxide, which are crucial for understanding the potential habitability of exoplanets. In conclusion, HD 100,546b's size and composition make it one of the most fascinating exoplanets discovered to date. Its massive size, dynamic atmosphere, and ongoing growth process provide scientists with a rare opportunity to study the early stages of planetary formation in a gas giant. As more observations are made and technology continues to improve, we are likely to gain even greater insights into the nature of this giant planet and the processes that shape its atmosphere, mass, and composition. Exploring other large exoplanets. While HD 100,546b stands out as one of the largest exoplanets discovered so far, it is far from the only massive world found in the vast universe. The search for giant exoplanets has unveiled a variety of gas giants, super-Earths, and other planetary types that challenge our understanding of planetary formation, migration, and the conditions under which planets can grow to enormous sizes. In this section, we will explore some of the other large exoplanets that rival or exceed HD 100,546b, examine what makes them unique, and consider what these planets can teach us about the processes that shape the universe. WASP-17b, a giant among giants. One of the most famous and intriguing large exoplanets discovered is WASP-17b, a gas giant located around 1,000 light-years away from Earth in the constellation Scorpius. WASP-17b was discovered in 2009 using the radial velocity method, and it quickly became the subject of much scientific interest due to its extraordinary size and low density. WASP-17b is about twice the size of Jupiter, making it one of the largest exoplanets in terms of diameter, but what truly sets it apart is its extremely low density. Despite its enormous size, WASP-17b has only about half the mass of Jupiter, making it one of the least dense exoplanets ever discovered. This unusual combination of size and low density suggests that WASP-17b is a gas giant with a very thin atmosphere compared to other planets of similar size. The low density of WASP-17b is likely the result of its rapid rotation. The planet is thought to complete a full rotation in just over 24 hours, causing the planet to flatten at the poles and expand at the equator. This shape, known as an oblate spheroid, is characteristic of planets that are experiencing extremely fast rotations. WASP-17b's size and low density have raised important questions about how gas giants form and how they retain their mass. Unlike Jupiter and Saturn, which formed much farther from their stars and slowly accreted gas from the surrounding nebula, WASP-17b is an example of a planet that likely formed very close to its star, within the hot, inner regions of its star system. The intense radiation and gravitational forces from the parent star may have played a significant role in shaping the planet's structure, preventing it from accumulating a denser atmosphere like that of Jupiter. WASP-17b's unusual characteristics make it an important object of study for astronomers, as it challenges traditional models of gas giant formation and helps scientists understand the impact of a star's proximity on the evolution of a planet. Its discovery also highlights the diversity of gas giants, demonstrating that they are not all formed or structured in the same way. WASP-12b, a planet on the edge. Another large exoplanet that has captured the attention of astronomers is located about 400 light-years from Earth in the constellation Auriga. This gas giant is one of the most extreme exoplanets discovered to date due to its extremely close orbit around its parent star, which is a hot F-type star. WASP-12b orbits its star in just 1.1 days, making it one of the fastest orbiting exoplanets known. The proximity of WASP-12b to its star causes it to experience intense tidal forces that distort its shape and cause its atmosphere to be pulled away into space over time. What makes particularly interesting is its extremely high temperature. The planet's proximity to its star means that it is constantly exposed to incredibly high levels of radiation, which heats the planet to temperatures around 500 degrees C, 500 degrees F, hot enough to melt metal. This extreme temperature has significant consequences for the planet's atmosphere, which is thought to be composed of hydrogen, helium, and a variety of heavier elements, including carbon and oxygen. The heat causes the atmosphere to expand, and some of the gases escape into space, contributing to the planet's mass loss over time. Is an example of an ultra-hot Jupiter, a type of gas giant that orbits incredibly close to its parent star. These planets are characterized by extreme temperatures and rapid orbital periods, and their study provides valuable insights into the effects of stellar radiation on planetary atmospheres. The discovery of WASP-12b and other ultra-hot Jupiters has led astronomers to develop new models of planetary atmospheres that account for the intense conditions these planets experience. The planet's extreme environment also raises questions about the limits of planetary survival. As WASP-12b continues to lose mass due to the intense radiation from its star, it may eventually reach a point where its atmosphere is stripped away entirely. This process, known as evaporation, is a key factor in determining the lifespan of hot Jupiters like WASP-12b, and it has significant implications for understanding the future of planets in close orbits. Kelt 9b, the hottest planet ever discovered. One of the most extreme and fascinating planets discovered in recent years is Kelt 9b, located around 650 light-years from Earth in the constellation Cygnus. Kelt 9b is an ultra-hot Jupiter that holds the record for the hottest planet ever discovered, with surface temperatures that reach up to 300 degrees C, 800 degrees F, hotter than the surface of some stars. This extreme temperature is a result of Kelt 9b's extremely close orbit to its parent star, an F-type star that is much hotter than our Sun. The planet orbits its star in just 1.5 days, which means it is subjected to intense radiation that causes its atmosphere to evaporate into space. Kelt 9b's surface temperature is so high that it is hotter than many stars. The planet is thought to have an atmosphere rich in alkali metals like sodium and potassium, which are vaporized by the intense heat. This has made Kelt 9b a prime target for studying the composition of exoplanetary atmospheres under extreme conditions. The planet's unusual temperature and atmospheric composition provide valuable insights into how stars and planets interact, particularly in star systems with planets that are in extremely close orbits. Kelt 9b's extreme environment has sparked interest in understanding how such planets form and what factors allow them to survive in such hostile conditions. Unlike other gas giants in more typical orbits, Kelt 9b's close proximity to its star means that it is constantly exposed to radiation levels that would render life, as we know it, impossible. However, the study of Kelt 9b and other ultra-hot Jupiters helps astronomers develop a deeper understanding of the range of conditions that planets can survive under and how they evolve over time. The diversity of large exoplanets. The discovery of planets like HD 100,546b, WASP 17b, WASP 12b, and Kelt 9b highlights the incredible diversity of large exoplanets in the universe. These planets are characterized by their massive sizes, extreme temperatures, and often unusual compositions. Each of these planets presents a unique set of conditions that challenge our understanding of planetary formation and evolution. The study of these giant worlds helps astronomers refine their models of planetary growth, migration, and atmospheric dynamics, and it opens up new questions about the processes that shape the diversity of planetary systems across the galaxy. While many of these massive exoplanets are gas giants, others, like super-Earths, provide a glimpse into the wide range of planetary types that exist. As our observational techniques improve and more exoplanets are discovered, the variety of worlds we encounter will only continue to expand. These discoveries challenge traditional models of planetary formation, forcing astronomers to rethink what is possible when it comes to the size, composition, and environments of planets. The search for the largest planets ever discovered will continue to push the boundaries of our knowledge, and with the upcoming launch of the James Webb Space Telescope, JWST, we are poised to explore these massive worlds in greater detail than ever before. As we continue to study these extraordinary exoplanets, we will gain deeper insights into the mechanics of planet formation, the diversity of planetary systems, and the conditions that allow planets to grow to such extreme sizes. The possibility of even larger planets. As astronomers continue to discover more massive exoplanets, one of the most intriguing questions that arise is whether we could encounter planets even larger than those we've already found. The discovery of massive worlds like HD 100,546b, WASP 17b, and Kelt 9b has led scientists to rethink the boundaries of planetary size. While these planets are already vastly larger than the ones we see in our solar system, there is still a possibility that much larger planets could exist, hiding in the far reaches of distant star systems, waiting to be discovered. The concept of a planet growing larger than anything we've observed so far requires a deeper exploration of planetary formation and the processes that allow a planet to accumulate mass. Planets form from the accumulation of gas, dust, and other materials in the protoplanetary disk surrounding a star. The larger the amount of material available in the disk, the greater the potential for a planet to grow. This process of planetary accretion is influenced by a variety of factors, including the star's size, the distance between the planet and the star, and the overall amount of material present in the system. One of the key questions in understanding the limits of planetary growth is how large a planet can get before it reaches a critical point where further growth becomes increasingly difficult. For gas giants like Jupiter and Saturn, the size of the planet is largely determined by the amount of gas in the protoplanetary disk. As these planets continue to accrete gas, they grow in size, but at a certain point, their growth slows down. The physical properties of the gas and the planet's own gravity play a significant role in this process. A planet's gravity must be strong enough to hold onto the gases it is collecting. If the planet becomes too large, the gas it is trying to capture may escape into space, preventing further growth. For instance, some astronomers believe that gas giants like Jupiter and Saturn may have grown to their current sizes because they were able to accumulate large amounts of hydrogen and helium from the surrounding disk before these elements were blown away by the star's radiation. Once the star reaches a certain age and begins to emit intense ultraviolet radiation, it can start to strip away the lighter elements from the planet's atmosphere. This phenomenon could create an upper limit on the size of gas giants. However, this process may be different in other star systems, depending on the amount of material available in the surrounding disk, the type of star, and the gravitational forces at play. The possibility of larger planets also depends on the balance between the planet's mass and its density. As planets accumulate more mass, their gravity increases and they begin to pull in more gas and dust. However, the more massive a planet becomes, the more difficult it is to maintain a low density. Gas giants like Jupiter are relatively low in density because they are composed mostly of light gases, such as hydrogen and helium. If a planet continues to grow, it may eventually become more dense, causing it to change in composition. At some point, the planet may transition from being a gas giant to a more solid planet, with a composition similar to that of ice giants like Uranus and Neptune. One aspect of planetary growth that remains a subject of much debate among astronomers is the role of runaway accretion. Runaway accretion is the process by which a planet rapidly accretes material from its surrounding disk, accelerating its growth. This can happen when a planet's core reaches a certain size, allowing it to attract large amounts of gas from the protoplanetary disk. This rapid accumulation of material can lead to the formation of supermassive planets that are much larger than anything seen in our solar system. Theoretically, if a planet's core continues to grow rapidly enough, it could reach a size much larger than Jupiter, potentially resulting in a planet that is several times more massive than the gas giants we are familiar with. The existence of even larger planets may be possible, especially in systems with abundant material and favorable conditions. A key factor in this process is the amount of gas available in the protoplanetary disk. Some star systems may have more material in their disks than others, allowing planets to grow to enormous sizes. In these systems, gas giants may continue to accrete material for a longer period of time, potentially leading to the formation of supermassive planets. Another factor that could play a role in the growth of larger planets is the presence of other planets in the system. In some cases, gravitational interactions between multiple planets can influence the migration of planets within their star system, potentially allowing for more material to be funneled onto a particular planet. This process could lead to the rapid growth of one planet at the expense of others, resulting in the formation of a supermassive world. The interaction between multiple planets in a system is still not fully understood, but it could offer an explanation for the formation of larger planets in some star systems. Theoretical models and limits on planet size. While the possibility of larger planets is intriguing, there are theoretical limits to how big a planet can grow. One of the main constraints is the planet's ability to retain gas. As a planet grows larger, its gravity increases and it begins to pull in more gas from the surrounding disk. However, there are limits to how much gas a planet can retain, particularly when it reaches a certain mass. Once the planet's mass becomes large enough, the radiation from the star could cause the planet's atmosphere to escape, preventing further growth. Another constraint is the planet's internal composition. Gas giants are primarily composed of hydrogen and helium, which are light elements that are relatively easy to accumulate. However, as a planet grows larger, it may begin to transition into a more solid structure, similar to the ice giants Uranus and Neptune. At this point, the planet's ability to continue growing by accreting gas becomes limited. The presence of heavier elements in the planet's core could eventually prevent further accretion, effectively capping the planet's size. Finally, the process of planetary migration also plays a role in determining the size of a planet. In many star systems, planets can migrate within their star systems due to gravitational interactions with other planets or the surrounding disk. This migration can affect the rate at which a planet accretes material and may ultimately influence the planet's size. Planets that migrate inward toward their parent star may not have the opportunity to grow as large as those that remain farther from their star. Additionally, the migration of planets could lead to the formation of more planets in a star system, further limiting the growth of any one planet. The search for larger planets. As our observational techniques improve and new telescopes come online, the search for even larger planets will continue. The James Webb Space Telescope, JWST, set to launch in the near future, will allow astronomers to observe exoplanets in unprecedented detail. JWST's advanced infrared capabilities will provide valuable data on the atmospheres, compositions, and environmental conditions of distant exoplanets, allowing scientists to search for planets that may be larger than anything we've discovered so far. By studying the characteristics of these planets, we may be able to determine whether they are still growing and what factors are influencing their development. The discovery of new exoplanets will also help us refine our understanding of the limits of planetary size. With more data on gas giants, super-Earths, and other types of planets, astronomers can test current models of planet formation and growth, providing deeper insights into the factors that determine how large a planet can become. These discoveries will not only expand our knowledge of planetary formation, but also offer new clues about the processes that govern the evolution of planetary systems. As we continue to explore the universe, the possibility of discovering even larger planets remains one of the most exciting prospects in astronomy. The sheer diversity of planetary types, the variety of star systems, and the ongoing development of new observational tools mean that the search for the largest planets will only intensify. Whether through direct imaging, spectroscopy, or future space missions, the discovery of even larger planets could unlock new chapters in the story of our universe, revealing the full extent of what is possible in the formation of worlds. What are the characteristics of massive planets? As we delve deeper into the study of the largest and most massive exoplanets in the universe, we begin to notice several unique characteristics that set these giants apart from the smaller, more familiar planets like Earth and Mars. Whether they are gas giants like Jupiter, ice giants like Uranus, or massive super-Earths, the massive planets discovered in distant star systems share common traits that reveal much about their formation, composition, and the environments they create. In this section, we will explore the defining characteristics of massive planets, the factors that shape them, and the extreme conditions that make them so different from the planets in our solar system. Atmosphere and composition. One of the most defining features of massive planets is their atmosphere. Most of the largest planets discovered, such as Jupiter, Saturn, and their exoplanet counterparts, are gas giants. These planets are primarily composed of light elements, with hydrogen and helium being the dominant components. In these gas giants, the atmosphere extends far beyond the planet's core and does not have a solid surface. The gas envelopes of these planets are often hundreds or even thousands of kilometers thick, filled with turbulent clouds and extreme weather systems, including the largest storms in the solar system. The composition of the atmosphere plays a critical role in determining the overall structure and properties of these massive planets. For instance, Jupiter's atmosphere is made up of clouds of ammonia, methane, and water vapor, giving it its distinctive banded appearance. Massive planets like Jupiter and Saturn also have dense atmospheres that trap heat and create powerful weather systems, such as Jupiter's famous Great Red Spot, a massive storm that has been raging for centuries. On the other hand, some massive exoplanets, like WASP-17b and HD 100546b, exhibit more extreme atmospheric conditions due to their proximity to their parent stars. These planets are located in hot regions where temperatures can reach unimaginable heights. The high temperatures on these planets cause their atmospheres to expand and escape into space, often resulting in extreme weather patterns, high winds, and the loss of atmospheric material. The ability of these planets to maintain their atmosphere despite such conditions is one of the key differences between gas giants and smaller planets, which often have more stable and less volatile environments. Size and density. The size and density of massive planets are also critical factors that distinguish them from smaller worlds. As discussed earlier, gas giants like Jupiter and Saturn are enormous in terms of their diameter, but are relatively low in density. This is because the vast majority of their mass is made up of hydrogen and helium, which are light elements. Their low density means that while they may appear large in size, their mass is not as concentrated as that of rocky planets like Earth. Massive exoplanets that fall into the category of superjupiters often display similar characteristics, with huge diameters and relatively low densities. For example, WASP-17b has a diameter twice that of Jupiter, but its density is much lower due to the lack of a solid core and its extended, less dense atmosphere. Despite being incredibly large, these planets are not as massive as their size would suggest, and their lower densities make them unique among planetary types. In contrast, ice giants like Uranus and Neptune in our solar system are not as massive as gas giants, but they still have a relatively high density compared to Jupiter and Saturn. These planets are primarily composed of water, ammonia, and methane ices and gases. Their atmosphere is thick, but their density is higher because they contain more rock and ice compared to gas giants. Many exoplanets, particularly those that are larger than Earth but smaller than Neptune, belong to a class known as super-Earths, which are also relatively dense and often have a composition that is more similar to Earth's. These planets are generally composed of rock, ice, and heavier gases, giving them a more solid structure compared to the gas giants. The size-to-density relationship is an important factor in determining how planets evolve. The more massive a planet becomes, the more gravity it exerts, which affects its internal structure and atmospheric composition. As planets grow in size, they experience increased pressure, which leads to the compression of their atmospheres and interiors. In gas giants, this pressure creates extreme weather systems and causes the planet's core to heat up. In contrast, smaller planets with a more solid composition experience less gravitational compression, which results in a less dense atmosphere and a more stable surface. Magnetic field. One of the key features of many massive planets is the presence of an intense magnetic field. Both Jupiter and Saturn have extremely powerful magnetic fields, which are generated by the movement of electrically conductive materials in their interiors. These magnetic fields are responsible for the creation of strong radiation belts and the characteristic auroras observed at the poles of these planets. Similarly, many of the largest exoplanets also exhibit strong magnetic fields, which are crucial for protecting the planet from harmful stellar radiation. The magnetic field of a massive planet plays a significant role in shaping its space environment. It helps to deflect high-energy particles from the star and prevents the planet's atmosphere from being stripped away by stellar winds. For example, Jupiter's magnetic field is so strong that it creates a radiation belt filled with charged particles, making the planet's surrounding space environment hostile to spacecraft. This magnetic field is an important aspect of the planet's overall structure, as it helps to protect the planet's atmosphere and maintain its stability over time. For exoplanets, studying the magnetic fields of massive planets can provide valuable insights into their interior composition and how they interact with their star systems. In some cases, The strength and behavior of a planet's magnetic field can help astronomers determine whether the planet has a liquid metal core, which is necessary for generating a strong magnetic field. This makes the study of magnetic fields a critical component of exoplanet research, as it can reveal much about the planet's structure and its potential for hosting life. Extreme weather systems. Massive planets, especially gas giants and hot Jupiters, are known for their extreme weather systems. On planets like Jupiter, Saturn, and their exoplanet counterparts, these systems are driven by a combination of the planet's internal heat, its rapid rotation, and the interactions between its atmosphere and the radiation it receives from its star. One of the most famous examples of extreme weather on a massive planet is Jupiter's Great Red Spot, a massive storm that has been raging for centuries. This storm is so large that it could fit 3 Earths inside of it, and it is just one example of the kinds of storms and atmospheric phenomena that occur on these giant planets. On exoplanets like WASP-17b, which is much closer to its parent star than Jupiter is to the Sun, extreme weather conditions are even more pronounced. The high temperatures on these planets lead to the development of strong winds, violent storms, and intense atmospheric circulation patterns. The immense size of the planet means that these weather systems can span large portions of the atmosphere and lead to dramatic weather events. On these hot Jupiters, the weather systems are driven by intense heat, and the storms can be far more extreme than anything seen on Earth. Habitable zones and potential for life. While the massive planets themselves are not likely to be habitable due to their hostile environments, their moons may hold potential for life. Many of the gas giants in our solar system, such as Jupiter and Saturn, have moons with environments that could support life, or at least microbial life, beneath their frozen surfaces. For example, Europa, one of Jupiter's moons, is thought to have a subsurface ocean beneath its icy crust that could harbor life. Similarly, some of the large exoplanets discovered in other star systems may have moons with conditions conducive to life. For instance, some of the super-Earths in the habitable zone of their stars are thought to have moons with atmospheres and conditions that could support life. While the massive planets themselves may not be suitable for life, their moons could provide a more hospitable environment, and the study of these moons will continue to be a key area of research in the search for life beyond Earth. Impact of large planets on their star systems. Massive planets, especially gas giants and super-Earths, can have a profound impact on the star systems in which they reside. These colossal worlds, with their immense size and gravitational pull, can significantly influence the formation, evolution, and dynamics of the planetary systems they belong to. Whether they are altering the orbits of nearby planets, shifting the location of asteroids and comets, or even influencing the characteristics of a star system's protoplanetary disk, the gravitational forces exerted by large planets play a crucial role in shaping the structure of their star systems. In this section, we will explore how these massive planets affect their star systems and the surrounding objects, highlighting the far-reaching consequences of their presence. Gravitational influence on planetary orbits. One of the most immediate and noticeable impacts that large planets have on their star systems is their gravitational influence on the orbits of other planets. As the mass of a planet increases, so too does its gravitational pull, which can cause the orbits of nearby planets to shift. This effect is particularly pronounced in systems with multiple large planets or super-Earths that are in relatively close proximity to one another. The gravitational interactions between these planets can lead to changes in their orbital periods, eccentricities, and even the direction of their orbits. In some cases, these gravitational interactions can lead to orbital migration, a phenomenon where a planet shifts from its original orbit to a new one. This migration can occur over time as the planet's gravity interacts with the surrounding material in the protoplanetary disk or with other planets in the system. In certain scenarios, large planets may migrate inward toward their star, while others may migrate outward. This migration can significantly alter the structure of a planetary system, potentially affecting the stability of the system and the position of planets within it. It can also lead to the ejection of smaller planets, asteroids, and comets from the system, reshaping the system's overall architecture. For example, in our own solar system, Jupiter's massive gravity has been linked to the formation of the asteroid belt between Mars and Jupiter. It is believed that Jupiter's gravity prevented the material in this region from coalescing into a full-fledged planet, leading to the formation of a scattered belt of smaller objects. Similarly, Jupiter's influence on the orbits of comets and asteroids has shaped the structure of the solar system and influenced the trajectory of many space objects. In exoplanetary systems, the gravitational effects of large planets on their neighboring planets can lead to resonances between their orbits. These resonances occur when two or more planets exert periodic gravitational forces on each other, causing their orbits to become synchronized. These interactions can result in a variety of orbital patterns, from stable, circular orbits to more eccentric and chaotic ones. Understanding these resonances is crucial for astronomers, as they can have significant implications for the long-term stability and evolution of a planetary system. Migration and disk interactions. The migration of large planets is not limited to their gravitational interactions with other planets. A planet's movement can also be influenced by the material in the surrounding protoplanetary disk. When a massive planet forms within the disk, its gravity can cause the disk material to shift, leading to the planet's migration either toward the star or away from it. This phenomenon is known as disk-driven migration. As a planet accretes material from the surrounding disk, it exerts a gravitational force that causes the disk to respond. In some cases, the interaction between the planet and the disk can cause the planet to move inward toward the star, where it can grow even larger by accreting more gas and dust. In other cases, the planet may migrate outward as the disk material moves away from the star. The migration of large planets can have significant consequences for the rest of the star system. For instance, planets that migrate inward may encounter other planets, potentially leading to collisions or changes in the system's overall architecture. Conversely, planets that migrate outward may destabilize the orbits of smaller planets and objects in the system, causing them to be ejected into space. In systems with multiple massive planets, their interactions with the disk and with each other can lead to dynamical instabilities in which the gravitational forces of the planets push them into chaotic orbits. This can result in the ejection of planets or the scattering of smaller objects throughout the system. Such interactions could potentially affect the habitability of planets within the system, particularly those located in the habitable zone, which is the region around the star where conditions may be suitable for liquid water to exist. Formation of moons and rings. Large planets are also known to have a significant influence on the formation of moons and rings around them. The gravity of a massive planet can capture nearby objects, such as asteroids or comets, and pull them into orbit, leading to the formation of moons. In our own solar system, Jupiter and Saturn have dozens of moons, ranging from small, irregularly shaped objects to large, spherical moons like Ganymede and Titan. In exoplanetary systems, large planets are similarly expected to have large moons, especially if they are gas giants. These moons can play an important role in the dynamics of the star system, as they can influence the planet's gravitational field and help stabilize its orbit. The formation of moons and rings is closely tied to the planet's ability to capture material from its surroundings, and the gravitational interactions between the planet and its moons can lead to the formation of complex ring systems, as seen around Saturn and Uranus. The moons of large planets can also have their own dynamics, including tidal interactions with their parent planet. These interactions can lead to phenomena such as tidal heating, where the gravitational forces between the planet and its moons create internal friction, causing the moons to heat up. This heating can have important consequences for the geological activity of moons, potentially leading to volcanic eruptions or the creation of subsurface oceans, which could increase the potential for life to exist on these moons. Effect on the star's radiation and stellar wind. Massive planets can also influence the star at the center of their system, particularly in terms of how the planet interacts with the stellar wind and the radiation emitted by the star. In many star systems, the presence of a large planet can help to shield the inner planets from the full force of the star's radiation. This occurs because the large planet's strong magnetic field can deflect high-energy particles, protecting the planets within its system from harmful radiation. In some cases, however, massive planets can experience the opposite effect, where the intense radiation from their parent star can strip away their atmosphere over time. This is especially true for planets that are in close orbits around their stars, such as hot Jupiters and ultra-hot Jupiters. The strong radiation from the star can cause the planet's atmosphere to evaporate, stripping away lighter gases and leading to the loss of mass. The interaction between a massive planet and its star can also lead to the creation of astrophysical phenomena such as planetary nebulae and magnetic interactions. These phenomena can influence the surrounding star system, potentially affecting the formation of other planets, moons, and objects in the system. The future of planet discovery. The search for planets beyond our solar system has experienced exponential growth in the past few decades, and the future of planet discovery looks incredibly promising. With the help of advanced space telescopes, groundbreaking observational methods, and improved computational techniques, astronomers are poised to discover even more planets, especially those that push the boundaries of size, mass, and distance. As we venture deeper into the cosmos, we will not only uncover larger planets, but also refine our understanding of how planets form, how they evolve, and the potential for finding habitable worlds that may host life. In this section, we will explore the exciting future of planet discovery, focusing on the tools, techniques, and missions that will shape the next chapter in exoplanet exploration. The James Webb Space Telescope, JWST. One of the most highly anticipated tools for the future of planet discovery is the James Webb Space Telescope, JWST, which is set to revolutionize our understanding of exoplanets. Scheduled for launch in the near future, JWST will have the ability to observe planets in unprecedented detail. With a focus on studying their atmospheres, compositions, and potential habitability, JWST is equipped with advanced infrared capabilities, allowing it to peer into the far reaches of the universe and detect exoplanets that are too faint or distant to be observed with current telescopes. JWST will be able to study the atmospheres of exoplanets in great detail by analyzing the light that passes through them during transits, which occurs when a planet moves across the face of its star. By studying the spectrum of light that filters through the planet's atmosphere, astronomers can determine its composition, temperature, and the presence of molecules like water vapor, carbon dioxide, and methane, key ingredients for life as we know it. This capability will be invaluable for studying the largest and most distant planets, as well as those located in the habitable zones of their stars, where liquid water may exist. JWST's ability to observe distant, faint exoplanets, along with its infrared capabilities, will also make it an essential tool for studying the atmospheres of gas giants, super-Earths, and even potentially habitable worlds. With the power to study exoplanets in greater detail than ever before, JWST is poised to unlock new insights into the conditions that make planets hospitable to life. Next-generation, ground-based telescopes. While space telescopes like JWST will undoubtedly play a crucial role in the future of planet discovery, ground-based telescopes are also evolving to meet the demands of exoplanet research. Several next-generation ground-based telescopes are currently in development, each designed to enhance our ability to detect and study exoplanets with greater precision. One of the most exciting of these upcoming telescopes is the Extremely Large Telescope, ELT, currently being constructed by the European Southern Observatory, ESO, in Chile. When completed, the ELT will have a primary mirror that is more than 39 meters in diameter, making it the largest optical and infrared telescope in the world. The ELT's size and capabilities will allow it to observe exoplanets in greater detail than ever before, providing high-resolution images of planets and their atmospheres, as well as the ability to study the planets in multi-wavelength bands from optical to infrared. Another important ground-based observatory is the 30-meter telescope, TMT, which is also being constructed in Chile. Similar to the ELT, the TMT will have an exceptionally large mirror, enabling it to study distant exoplanets and star systems with unparalleled detail. The TMT will focus on observing the atmospheres of exoplanets, including those in the habitable zone, as well as conducting surveys of exoplanet populations in nearby star systems. Together with the ELT, the TMT will provide a powerful set of tools for future exoplanet discoveries, complementing space-based missions like JWST. Advanced detection techniques. As the technology used to detect exoplanets continues to advance, astronomers are developing new and innovative techniques that will allow us to find even more distant, smaller, and harder to detect planets. While traditional methods like radial velocity and transit have been incredibly successful in detecting large, massive exoplanets, the future of planet discovery lies in the ability to detect smaller planets, particularly those that are Earth-like in size and composition. One promising technique for detecting these smaller exoplanets is direct imaging. Direct imaging allows astronomers to capture images of exoplanets by blocking out the light from their parent stars. This method is particularly effective for observing large planets that are far from their stars, as the light from the star can overwhelm the faint light emitted by the planet. In the future, high-contrast imaging systems, coupled with advanced coronagraphs or starshades, will allow astronomers to observe planets directly, even those in close orbits around their stars. This technique will also provide valuable data on the planet's atmosphere, surface, and potential for life. Gravitational microlensing is another exciting technique that will play a key role in future planet discovery. This method involves detecting the bending of light caused by the gravitational field of a planet or star as it passes in front of a more distant background star. By measuring the way light is distorted during this event, astronomers can determine the mass and location of the planet, as well as its orbit. Microlensing has been used to detect exoplanets that are too faint or distant to observe using other methods, and it has the potential to reveal large populations of exoplanets in distant parts of the galaxy. The search for Earth-like exoplanets. One of the most exciting goals in the future of planet discovery is the search for Earth-like exoplanets, planets that have conditions similar to those on our own world and that could potentially harbor life. While scientists have already discovered a number of planets in the habitable zone of their stars, the region where liquid water can exist, we are still a long way from understanding which of these planets might truly be Earth-like in composition and environment. Future missions such as TESS, Transiting Exoplanet Survey Satellite, and Plato planetary transits and oscillations of stars will play a critical role in identifying Earth-like planets in nearby star systems. TESS, launched in 2018, is already conducting a comprehensive survey of nearby stars, searching for exoplanets that may be similar in size and orbit to Earth. Plato, which is expected to launch in the near future, will focus on studying planetary systems in even greater detail, looking for planets that are Earth-sized and located in the habitable zone of their stars. While JWST will be instrumental in studying the atmospheres of exoplanets, future missions will need to focus on refining our models of habitability. Scientists will need to learn more about the composition of these planets' atmospheres, their surface conditions, and the possibility of water and other life-sustaining resources. The ultimate goal is to identify planets that could support life, whether microbial or complex, offering a glimpse into the potential for life beyond Earth. The role of artificial intelligence in exoplanet discovery. As we venture into a future of increasingly complex data sets, artificial intelligence, AI, is poised to become a crucial tool in the search for new exoplanets. The sheer volume of data produced by space telescopes and observatories is overwhelming, and traditional methods of data analysis are no longer sufficient to handle it all. AI, particularly machine learning algorithms, will help astronomers sift through vast amounts of data, identifying patterns and anomalies that might otherwise go unnoticed. AI can assist in a variety of ways, from automating the detection of exoplanet transits to analyzing complex atmospheric data. Machine learning models can also help to identify exoplanet candidates by recognizing patterns in light curves, making it easier to identify potential planets for further observation. As the field of exoplanet discovery becomes more data-intensive, AI will play a key role in helping scientists make sense of the information and accelerate the pace of discovery. The implications of discovering large planets. The discovery of large exoplanets, particularly those that exceed the size and mass of Jupiter, has far-reaching implications for our understanding of the universe. These massive worlds challenge many of the assumptions we once had about planetary formation, the limits of size, and the potential for life beyond Earth. As astronomers continue to find and study these giant exoplanets, they uncover not only the dynamics of planetary systems, but also deeper insights into the fundamental processes that shape stars, planetary systems, and the evolution of the cosmos. Planet formation and evolution. One of the most significant implications of discovering large exoplanets is the insight it provides into the processes of planet formation and evolution. The size of a planet plays a critical role in its formation. While smaller, rocky planets like Earth form through the gradual accumulation of dust and rock, gas giants like Jupiter and Saturn, along with their massive exoplanet counterparts, form through a combination of accretion and the accumulation of gas from the surrounding protoplanetary disk. The discovery of massive planets challenges our understanding of how planets grow and evolve. For instance, in traditional models of planetary formation, gas giants are believed to form far from their parent stars, where the temperatures are cooler, allowing gas to condense into the planet's massive atmosphere. However, the discovery of hot Jupiters, such as WASP-17b and HD 100546b, which orbit extremely close to their stars, challenges this theory. These planets defy our expectations of where gas giants should form and raise new questions about how planetary migration and disk interactions allow for such planets to exist in the inner regions of star systems. The discovery of large exoplanets is particularly important for understanding the limits of planetary growth. How big can a planet really get? As we discover more gas giants and supermassive planets, scientists are forced to reconsider the theoretical limits on planetary size. Are there physical constraints on how large a planet can grow before it becomes unstable? The discovery of planets like HD 100546b, which are still growing and accumulating material, is providing a rare glimpse into the early stages of planetary evolution and helping to refine models of how planets grow to such extreme sizes. Diversity of planetary systems. The discovery of massive planets also underscores the incredible diversity of planetary systems in the universe. Our solar system is relatively typical, with a small rocky planet near the star and larger gas giants farther out. However, as we observe more exoplanets, we find that planetary systems can vary widely. Some systems contain multiple gas giants in close orbits, while others have super-Earths that may have conditions more similar to Earth than anything found in our own solar system. The presence of large planets in these systems raises new questions about the formation and architecture of planetary systems. Could a gas giant like HD 100546b serve as a regulator of its star system, affecting the orbits of smaller planets and asteroids? Or could the migration of a massive planet disrupt the stability of a planetary system, ejecting smaller planets or moons into space? The interactions between large planets and the rest of the star system may also have implications for the potential for life on smaller, Earth-like planets. If massive planets are capable of migrating, how might this affect the positions and orbits of potentially habitable planets? These questions about the dynamics of planetary systems are central to the ongoing exploration of the universe. The discoveries of gas giants, hot Jupiters, and super-Earths in distant systems have shown that planets can exist in a multitude of forms and sizes, which in turn affects the overall structure of their star systems. The study of these systems helps us understand how planets evolve, how they interact with one another, and how the environments around stars shape the formation of planetary systems. Planetary habitability and the search for life. While large gas giants like Jupiter and Saturn are unlikely to harbor life as we know it, the discovery of massive exoplanets has profound implications for the search for life elsewhere in the universe. Super-Earths, planets that are larger than Earth but smaller than Neptune, are especially intriguing in this context, as they offer a unique opportunity to study planets that could potentially have conditions conducive to life. Super-Earths are typically rocky planets that may have atmospheres capable of supporting liquid water. These planets are often found in the habitable zones of their stars, where conditions may be just right for life to thrive. The discovery of super-Earths in nearby star systems has accelerated the search for planets that are not only Earth-sized, but also in the Goldilocks zone, where they are neither too hot nor too cold. While these super-Earths are not as massive as gas giants, their size and composition make them more likely candidates for habitability than the largest gas giants. The study of planetary atmospheres on super-Earths and other large exoplanets also plays a key role in understanding their potential for hosting life. The detection of biosignatures, indicators of life, on the atmospheres of distant exoplanets is a major goal of future missions. Instruments like the James Webb Space Telescope will help astronomers analyze the atmospheres of exoplanets, looking for signs of water vapor, oxygen, methane, and carbon dioxide, all of which are essential components for life as we know it. Furthermore, the discovery of moons orbiting large exoplanets adds another layer of possibility for life beyond Earth. Large planets like Jupiter and Saturn in our solar system have numerous moons, some of which are thought to have subsurface oceans where microbial life could potentially exist. In the same way, moons orbiting exoplanets, particularly super-Earths or gas giants, may also provide habitable environments for life to develop, and scientists are already investigating the potential for finding life on these moons. Planetary protection and exploration. As we continue to discover more massive planets and exoplanets, the question of planetary protection becomes more pressing. As space exploration progresses, we may eventually send probes or even humans to explore these distant planets. Ensuring that we do not contaminate other planets with Earth-based microorganisms or introduce foreign organisms to our own planet is a critical concern for future space missions. Planetary protection measures are designed to ensure that space missions are conducted in a way that prevents the unintended transfer of organisms between planets. This includes sterilizing spacecraft and equipment before they launch to minimize the risk of contamination. As we develop the technology to explore exoplanets and their moons, these protocols will be essential to maintaining the integrity of scientific research and protecting both Earth and other planets from cross-contamination. Technological advancements and the future of exploration. The future of planet discovery will depend on continued technological advancements. As telescopes and observational instruments improve, our ability to detect and study exoplanets will become more precise. In the near future, missions such as the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, will provide us with the tools to detect and study even smaller and more distant exoplanets. These missions will help to further characterize the atmospheres, compositions, and potential habitability of exoplanets, as well as deepen our understanding of planetary systems across the galaxy. Moreover, as computational power increases, simulations of planetary formation and evolution will become more sophisticated, allowing us to predict the characteristics of exoplanets and identify new targets for exploration. The development of AI and machine learning algorithms will also play a crucial role in the search for exoplanets by analyzing massive data sets from telescopes and identifying planets that may otherwise go unnoticed. The search for the largest planet. Final thoughts. The quest to discover the largest planet ever found is not just about size, it's about the profound implications these discoveries have for our understanding of the universe. As astronomers continue to push the boundaries of space exploration, they are uncovering planets that challenge our assumptions, expand our knowledge, and open new doors for future research. These massive worlds, ranging from gas giants like Jupiter to supermassive exoplanets like HD 100,546b, are reshaping our understanding of planetary formation, evolution, and the fundamental processes that drive the dynamics of star systems. Size as a tool for understanding planet formation. In many ways, the search for the largest planets serves as a tool to unlock the mysteries of planetary formation itself. The size of a planet is not just a measure of its physical dimensions. It is a reflection of the underlying processes that govern the accretion of material from the surrounding environment. Large planets, particularly gas giants, provide unique insights into the mechanisms that allow planets to form and grow in different star systems. The discovery of massive exoplanets, such as HD 100,546b and WASP-17b, challenges traditional models of planet formation, especially regarding the relationship between a planet's size, its position relative to its star, and the material available in the protoplanetary disk. For instance, hot Jupiters like WASP-17b, which orbit their stars at a distance much closer than Jupiter does from the Sun, force astronomers to reconsider the processes that allow gas giants to form in the first place. Understanding how these massive planets can grow and thrive in extreme environments is crucial for refining our models of planetary formation across the universe. Furthermore, the discovery of super-Earths, planets that are larger than Earth but smaller than gas giants like Neptune and Jupiter, adds another layer of complexity to our understanding. These planets, which may possess rocky compositions similar to Earth, challenge the notion that only small, rocky planets can form in the habitable zone of a star. Their existence has broad implications for the search for life, as super-Earths are often found in the habitable zones of their stars, where conditions may be conducive to liquid water. The study of large exoplanets helps scientists develop better models of how planets grow, migrate, and interact with their star systems. This ongoing research is fundamental to answering critical questions about planetary evolution, including the role of gravity, atmospheric composition, and stellar radiation in shaping a planet's development. Planetary migration and system architecture. One of the most significant discoveries in recent years has been the realization that large planets can migrate within their star systems, sometimes moving thousands of miles inward or outward over the course of millions of years. The migration of gas giants, such as HD 100,546b, challenges our previous understanding of planetary system architecture and the forces that shape the orbits of planets. In systems with multiple large planets, migration can significantly alter the orbits of smaller planets, potentially throwing them out of their stable positions or causing them to collide. For example, Jupiter's migration in the early history of our solar system is believed to have influenced the distribution of asteroids and comets, shaping the asteroid belt and preventing the formation of a fifth terrestrial planet between Mars and Jupiter. The discovery of exoplanets that have migrated from their initial formation zones has also altered our perception of planetary stability. Some of the largest exoplanets, such as WASP-17b and Kelt-9b, are found in highly eccentric orbits that suggest significant migration. The gravitational interactions between these giant planets and their star systems could provide insights into the long-term stability of planetary orbits and the potential for habitable planets to exist in systems with large migrating planets. The search for Earth-like planets and life beyond Earth. As the search for the largest planets continues, another key question emerges. How does the discovery of massive exoplanets impact the search for life beyond Earth? While massive gas giants like Jupiter and Saturn are unlikely to harbor life, the search for planets in the habitable zone, the region around a star where conditions may be right for liquid water to exist, is central to the quest for discovering life beyond our planet. The discovery of super-Earths in habitable zones is one of the most exciting developments in this regard. These planets, which may have atmospheres capable of supporting life, offer a new frontier in the search for extraterrestrial life. As we continue to discover more super-Earths, researchers are exploring the possibility that these planets could host microbial or even more complex forms of life, depending on their environmental conditions. The study of massive exoplanets also plays a crucial role in understanding how the environments around these planets can evolve over time. Some large planets, such as hot Jupiters, are constantly exposed to extreme radiation from their parent stars. Understanding how these planets interact with their stars can provide valuable insights into the behavior of planetary atmospheres, including how they retain or lose their atmospheres over time. In addition to the study of individual planets, the discovery of large planets also contributes to our broader understanding of planetary systems. By studying the interactions between massive planets and smaller worlds, astronomers can learn more about the conditions that make a system conducive to life. For example, the presence of large planets in a system can influence the potential habitability of nearby smaller planets, either by stabilizing their orbits or by causing chaos and ejecting them from the system. New technologies and methods for planetary discovery. Looking to the future, advances in technology will play a pivotal role in the ongoing search for the largest and most intriguing planets in the universe. New telescopes, such as the James Webb Space Telescope, JWST, will allow astronomers to observe exoplanets in greater detail, from studying their atmospheres to detecting potential signs of life. The ability to directly image exoplanets, study their atmospheres, and measure their mass and composition will provide unprecedented insights into the nature of these distant worlds. Additionally, improved observational techniques, such as gravitational microlensing and direct imaging, will allow astronomers to detect even more exoplanets, especially those that are located in distant parts of the galaxy. These techniques will be essential for identifying planets that are too faint or distant to be detected using traditional methods, such as the radial velocity or transit methods. The development of artificial intelligence, AI, will also play a key role in the future of planet discovery. AI algorithms will be used to analyze the massive amounts of data generated by observatories and space telescopes, helping scientists identify exoplanet candidates more efficiently and accurately. With AI, astronomers will be able to sift through vast data sets to uncover new and unexpected planetary discoveries. The continuing quest for the largest planet. As we continue our search for the largest planets in the universe, the discoveries we make will have profound implications for our understanding of the cosmos. From the formation of gas giants like Jupiter to the discovery of supermassive exoplanets in distant star systems, each new planet discovered challenges our assumptions and opens up new avenues of exploration. The future of planet discovery holds great promise. With new tools, innovative methods, and a growing understanding of planetary systems, we are on the cusp of uncovering even more giant exoplanets, some of which may be beyond our current imagination. These discoveries will not only provide insight into the limits of planetary size, but also help us answer some of the most fundamental questions about the universe, including the possibility of life beyond Earth. As we continue to explore the far reaches of space, the search for the largest planet is not just about the planets themselves, but about understanding the universe on a deeper level, how it formed, how it works, and how we fit into the grand expanse of time and space. The discoveries of the future are sure to provide answers to questions we've been asking for centuries, pushing the boundaries of human knowledge and inspiring the next generation of explorers. The role of large planets in the search for extraterrestrial life. As astronomers expand their search for habitable planets beyond our solar system, the discovery of large exoplanets has taken on new significance, particularly in the context of the search for extraterrestrial life. While massive gas giants like Jupiter and Saturn may not be suitable for hosting life themselves, their presence and the environments they create can still provide essential clues about the conditions necessary for life in the universe. In this section, we will explore how large planets play a role in the broader search for life beyond Earth, the indirect ways they influence the habitability of nearby planets, and their potential to host moons that may harbor life. Large planets as planetary system architects. Large planets, especially gas giants, play a crucial role in shaping the architecture of their entire star systems. Their immense gravity influences the orbits of smaller planets, asteroids, and comets, sometimes helping to stabilize or destabilize the system. For example, in our own solar system, Jupiter's gravity has had a profound impact on the distribution of smaller objects, such as the asteroid belt between Mars and Jupiter. Jupiter's gravitational pull likely prevented the material in the region from forming a planet, leaving behind the scattered collection of asteroids that we observe today. In some star systems, the presence of large planets may play a stabilizing role for smaller, Earth-like planets in the habitable zone. By preventing the inward migration of smaller bodies or altering the orbits of other planets, large gas giants may help keep smaller planets in stable orbits for long periods of time, creating conditions conducive to the development of life. The stabilization of a planet's orbit is essential for maintaining a steady climate, which is a key factor for habitability. Therefore, massive planets may indirectly promote the conditions necessary for life by regulating the movements of smaller, potentially habitable planets in their star systems. On the other hand, large planets can also disrupt the formation and stability of planetary systems, especially if they migrate or interact gravitationally with other planets. For example, planetary migration, in which a large planet moves inward or outward within its star system, can dramatically affect the orbits of smaller planets, potentially ejecting them from the habitable zone or altering their climates. Such disruptions can either create opportunities for life by opening up new regions for the formation of planets, or hinder the development of life by destabilizing existing planets. Gas giants and moon habitability. While massive gas giants themselves are unlikely to host life, their moons may provide more promising environments for habitability. In our solar system, some of the largest moons orbiting gas giants, such as Europa orbiting Jupiter and Titan orbiting Saturn, are thought to have the potential to support microbial life. These moons are believed to have subsurface oceans beneath their icy crusts, which could provide the necessary conditions for life to thrive. The potential for life on these moons, often referred to as habitable moons, underscores the importance of gas giants in the search for extraterrestrial life. For instance, Europa's subsurface ocean, kept warm by tidal heating from Jupiter's gravity, is a prime candidate for the search for life beyond Earth. Similarly, Titan, with its thick atmosphere and methane lakes, presents a unique environment where life could potentially exist in forms vastly different from those found on Earth. The presence of gas giants in star systems could increase the likelihood of such habitable moons, as their strong gravity helps capture and maintain objects in orbit, providing the stability required for moons to evolve and sustain environments conducive to life. The moons of large planets in other star systems may also hold promise for the search for life. If massive exoplanets have moons in the habitable zone of their stars, those moons could possess liquid water, an atmosphere, and the necessary ingredients for life. The discovery of exomoons is a burgeoning field of research, with astronomers using advanced telescopes and detection methods to identify moons that may be orbiting gas giants and super-Earths. These moons could be prime targets for future missions aimed at detecting signs of life. Large planets and stellar protection. Large planets, particularly gas giants, also play an important role in protecting smaller rocky planets from the harsh radiation emitted by their parent stars. In our solar system, Jupiter acts as a cosmic shield, protecting Earth and the inner planets from frequent impacts by asteroids and comets. The immense gravitational pull of Jupiter helps to divert potential threats from the asteroid belt, redirecting them away from Earth. This protection from cosmic debris has been crucial for the stability of life on our planet. In star systems with large planets, especially those with gas giants located farther from their parent stars, similar protection could exist for smaller planets in the habitable zone. By acting as gravitational shields, these massive planets could reduce the frequency of asteroid or comet impacts, creating a more stable environment for the development of life. The lack of such protection, on the other hand, could lead to an increase in planetary impacts, which may prevent life from establishing itself or disrupt the stability required for life to thrive. Additionally, large planets can influence the stellar wind, a stream of charged particles emitted by the star. Gas giants with strong magnetic fields can interact with stellar wind to create protective shields for nearby planets, including those in the habitable zone. These magnetic fields help deflect harmful radiation, creating a safer environment for life to evolve. The search for Earth-like planets, insights from large planets. While large exoplanets themselves may not be ideal candidates for the search for life, their study offers important insights into the search for Earth-like planets. By examining the characteristics of gas giants and super-Earths, astronomers can better understand the conditions under which planets of all sizes form and evolve. For example, studying how large exoplanets interact with their parent stars and the protoplanetary disks surrounding them can help scientists refine their models of planetary formation, especially in star systems where Earth-like planets may exist. The study of large exoplanets also helps astronomers narrow down the conditions required for habitability. As astronomers continue to study massive gas giants and their moons, they are learning more about the types of environments that could support life. This information is crucial for identifying which planets in the habitable zones of their stars have the potential to harbor life. In particular, the discovery of super-Earths in the habitable zones of nearby stars has brought us closer to identifying planets that are Earth-like in size, composition, and distance from their stars, factors that are essential for the potential development of life. The quest to find Earth-like planets is ongoing, and while large gas giants may not be the focus of this search, their role in shaping planetary systems is indispensable. By continuing to study the largest planets in distant star systems, astronomers are gradually piecing together the puzzle of how planets form, evolve, and potentially support life, one discovery at a time. Conclusion: the broader implications for the search for life. The search for large exoplanets has profound implications for the broader quest to understand the potential for life beyond Earth. While these massive worlds may not directly host life themselves, they influence the formation and dynamics of their star systems, which can affect the habitability of nearby planets and moons. From stabilizing planetary orbits to protecting inner planets from cosmic threats, large planets play a critical role in shaping the conditions necessary for life. The discovery of habitable moons, the protection of smaller planets from stellar radiation, and the insights gained from studying planetary systems with massive gas giants all contribute to our understanding of what makes a planet or moon capable of supporting life. The ongoing research into exoplanets, facilitated by powerful telescopes like the James Webb Space Telescope and ground-based observatories, will continue to push the boundaries of our knowledge and guide future missions to explore potentially habitable worlds. In the end, while the largest planets may not be candidates for life, they are integral to the bigger picture, the search for life beyond Earth. As we explore new star systems, the role of massive planets will continue to shape the way we approach the search for extraterrestrial life, bringing us ever closer to answering one of humanity's most profound questions: are we alone in the universe? The future of planetary exploration. As our understanding of exoplanets deepens, the future of planetary exploration holds immense promise. New technologies, sophisticated spacecraft, and ambitious missions will allow astronomers and space agencies to push the boundaries of discovery even further. The pursuit of the largest and most mysterious planets in the universe will continue to shape the field of astrophysics, planetary science, and our understanding of the cosmos. In this final section, we'll explore the exciting future of planetary exploration, including upcoming missions, technological advancements, and the role of international collaboration in unlocking the secrets of distant worlds. Advances in space telescope technology. The next generation of space telescopes promises to transform how we observe and study distant exoplanets. One of the most anticipated instruments for planetary exploration is the James Webb Space Telescope, JWST. Set to launch soon, JWST will provide unprecedented observational capabilities, allowing astronomers to peer deeper into space than ever before. The telescope will be equipped with infrared technology, enabling it to observe exoplanets in ways that were previously impossible. JWST's ability to detect the chemical makeup of exoplanet atmospheres, study their compositions, and detect possible signs of life will provide us with the most detailed data on planetary systems across the galaxy. JWST's ability to directly observe the spectral signatures of exoplanets during transits, when a planet passes in front of its star, will be crucial in identifying key biomarkers in their atmospheres. These findings will help scientists assess the potential habitability of exoplanets and detect whether conditions exist that could support life similar to Earth. The telescopic capabilities of JWST are expected to revolutionize our ability to detect not just the largest planets, but also those in the habitable zone of their stars, where life may be possible. Following in the footsteps of JWST, future missions such as the Nancy Grace Roman Space Telescope will expand our search for exoplanets even further, offering enhanced wide-field capabilities that will focus on planetary populations and investigate dark energy. The data gathered by JWST and Roman will be combined, providing a comprehensive view of planetary systems, from massive gas giants to potentially habitable exoplanets. Ground-based observatories, the Extremely Large Telescope, ELT. While space telescopes are essential for observing distant worlds, ground-based observatories will also continue to play a key role in planetary exploration. The Extremely Large Telescope, ELT, currently under construction by the European Southern Observatory, ESO, in Chile, will become the largest optical and infrared telescope in the world. With its 39-meter mirror, ELT will enable astronomers to capture images of exoplanets with unprecedented clarity. Its powerful spectroscopic capabilities will allow for detailed studies of exoplanet atmospheres, the detection of molecular compounds, and the possibility of finding signs of life. The ELT's size and advanced instruments will make it possible to observe distant exoplanets directly, including those in the habitable zones of their stars. As one of the largest ground-based telescopes ever constructed, the ELT will complement space missions by providing detailed follow-up observations and exploring aspects of planetary systems that space telescopes cannot easily study. Similarly, the 30-meter telescope, TMT, currently under development in Chile, will have a 30-meter mirror capable of studying distant exoplanets in greater detail. With a focus on the characterization of exoplanetary systems, TMT will assist in studying the atmospheres and climates of large exoplanets, as well as investigating the potential for habitable environments on super-Earths and other rocky planets. Direct imaging of exoplanets. One of the most exciting frontiers in planetary exploration is the ability to directly image exoplanets. While this has been a challenging task due to the overwhelming brightness of their parent stars, Advancements in coronography and starshades are helping to make this a reality. The use of starshades, which block the light from a star while allowing the light from an exoplanet to pass through, will revolutionize our ability to capture images of planets orbiting distant stars. This method, which uses a specially designed shield to block out the star's light, will allow astronomers to study the surface characteristics, atmospheric compositions, and weather patterns of exoplanets in greater detail. Direct imaging will be particularly valuable for studying large, distant exoplanets, especially gas giants and super-Earths. By capturing detailed images of these planets, scientists can gain insights into their atmospheric conditions, surface features, and potential for supporting life. The combination of direct imaging with other detection methods, such as spectroscopy and transit observation, will provide an in-depth understanding of planetary systems, offering a complete picture of how planets form, evolve, and interact with their stars. Planetary missions and space probes. In addition to observatories and telescopes, future planetary missions will play a key role in our exploration of exoplanets. One such mission is the Interstellar Probe, a conceptual spacecraft designed to travel beyond our solar system and explore the interstellar medium. This probe will eventually pass through regions of space where exoplanets reside, giving us the first close-up observations of distant planets in other star systems. In addition to interstellar missions, more targeted probes may be launched to explore specific exoplanets and their moons. While sending probes to exoplanets will be a monumental challenge due to the vast distances involved, the development of new propulsion technologies, such as nuclear fusion or light sails, may eventually allow us to send spacecraft on long-duration missions to nearby exoplanetary systems. Additionally, missions like LUVOIR, Large Ultraviolet Optical Infrared Surveyor, are being considered for the study of exoplanets in the future. LUVOIR would be capable of imaging distant worlds in various wavelengths, detecting water vapor, methane, and other potential biosignatures in the atmospheres of exoplanets. These upcoming space missions will provide unprecedented insight into the nature of distant planets, enhancing our ability to study planetary systems and their potential for supporting life. Artificial intelligence and data analysis. As the volume of data collected from planet detection missions continues to increase, artificial intelligence, AI, will play an increasingly important role in planetary discovery. With the help of machine learning algorithms, astronomers can analyze massive datasets from space telescopes, observatories, and planetary probes, identifying patterns and anomalies that may otherwise be overlooked. AI has already proven useful in exoplanet research by helping astronomers sort through vast amounts of data from the Kepler Space Telescope, leading to the discovery of new exoplanets. In the future, AI will be used to analyze data from a variety of sources, including the transits of exoplanets, the radial velocity method, and direct imaging techniques. Machine learning models can automate the process of identifying potential exoplanets, predicting the types of planets in a star's habitable zone, and even analyzing the potential for biosignatures in the atmospheres of distant worlds. AI's role in planetary exploration will allow for faster, more efficient discoveries, bringing us closer to answering questions about the possibility of life beyond Earth. The continuing search for life. Finally, the search for life remains one of the most compelling motivations for planetary exploration. As we discover more and more massive planets, gas giants, and super-Earths, we are also uncovering the diverse range of environments where life could potentially exist. Whether on an Earth-like exoplanet, a moon orbiting a gas giant, or a planet in the habitable zone of its star, the discovery of life beyond Earth is one of the most exciting prospects in science. Each new planet we discover brings us closer to answering the profound question, are we alone in the universe? With the combination of cutting-edge technology, international collaboration, and a relentless drive for discovery, the future of planetary exploration is bright. The next decade of exploration promises to reveal new exoplanets, new moons, and new insights into the forces that shape planetary systems. We may discover new worlds where life thrives, uncover the origins of our own solar system, and learn more about the forces that drive the evolution of stars and planets.